we are going to learn about the another new concept which is called as a 3-bit or 2-word ladder network. So this is basically, I have already told you, this is called as a DAC. So this is the one of the DAC here, means we are going to convert the digital input to the analog input. So now we will see how we are going to make this happen. So this is called as a 3-bit or 2-word ladder network, means it is a DAC type, means DAC means digital to analog conversion. So this is a circuit that you always have to keep in your mind. So this is a 3-bit or 2-word ladder network DAC. So this is called as the, so you can say this is a 2-word, this is a 2-word, this is a 2-word, and this is a 2-word. And between them there is a resistor R and resistor R here. So here we are going to give some reference voltage. So we are going to give some reference voltage, supply voltage like this. And here we are going to keep the switches. Here three switches we are going to keep. Let me assume this is the LSB, this is MSB. So farthest one is the MSB and this is called as the LSB, which is B0, B1 and B2. See, the resistor corresponding to green resistor 2R is LSB. So therefore, see, whatever this resistor is there, no, it's a green resistor. So the switch corresponding to this resistor is always LSB and the farthest one is called as the MSB. So this is B0, B1 and B2. So whatever the switch corresponding to 2R resistor is always a LSB and the farthest one is always a MSB. So this is a very important point that you always need to understand this concept. So I am going to tell you again. See, for this green resistor, whatever the switch which is corresponding to green resistor is always LSB. So resistor corresponding to green resistor 2R is LSB. So this is called as LSB. So whatever the switch corresponding to this green resistor is always called as LSB and the farthest one is called as the MSB. So now you can see clearly. See, switch is on means I am going to connect the switch to V reference. If the switch is off means I am going to connect the switch to ground. So these two things are possible. So whenever the switch is equal to on means 1, I am going to connect to V reference, and whenever the switch is off means I am going to connect to reference voltage of 0. So this is a circuit diagram that we are going to see 2R, 2R, 2R. Here there is a 2R. So this is the B0, B1, B2, LSB and MSB, and these are the two resistors connecting between these two junctions. So resistor R and resistor R. And this is the Vx voltage. Vx voltage we need to figure out. So with the help of this switching, we are converting this digital format into analog format. This is the basic agenda of this switching. So now calculation of Vx. So we are going to find what is the value of Vx. So Vx is nothing but Vx is equal to Vx2 plus Vx1 plus Vx0, means this voltage is summation of voltage because of only this is on or this is on plus this is on. It's a basically we can say it is a superposition theorem. So if then suppose only switch, if the MSB is on, then what is this voltage? Let me assume this is Vx2. If suppose only switch 1 is on, then what is the voltage? This is, let me assume this is Vx1. Suppose if only this switch B0 is on, then what is the voltage I am going to assume? This is Vx0. So by superposition, if all are on, then what is the overall Vx? It is a summation of voltage because of switch main switch MSB, then B1, then B0. So therefore, Vx is equal to Vx2 plus Vx1 plus Vx0. So Vx2 is nothing but it is the analog voltage whenever the only switch B2 is on, and Vx1 is the voltage analog voltage only when switch B1 is on, and Vx0 is the analog voltage only when switch B0 is on. So therefore, by the help of superposition, we have to add each and everything. So we are going to get the overall output voltage as Vx. So now I want to find the Vx. So if you want Vx, you have to find Vx2, Vx1 and Vx0. So first thing I will find what is Vx2. So Vx2 means I have already told you only switch 2 is on or MSB is on or switch B2 is on. So switch B2 is on means MSB is on. To on means we are going to keep it to V reference, and the remaining things we are going to keep it ground. So we are going to keep it to ground means we are basically off in the switches means we are going to keep it to ground. So these two switches we are going to keep it to ground. So now I want to find So now I will try to find what is this voltage Vx2. So Vx2 I will find with the help of, see, you can see clearly, these two are in parallel. So 2R is nothing but R plus R 2R, again parallel, again R. So R plus R again 2R. So 2R in series. So what is this voltage? Vx2 is equal to supply voltage by 2 by voltage division principle. So Vx2 is equal to V reference by 2. So therefore simply we can say generally Vx2 is equal to V reference by 2 into B2. B2 is the switching. So B2 is the switching. When B2 is on, then B2 is on means B2 is equal to 1. Then we are going to get V reference by 2. If switch B2 is off means we have to replace B2 is equal to 0, then we are going to get this as 0. So general expression of Vx2 is equal to V reference by 2 into B2. So this is an important expression that you always need to keep in your mind. So whenever the switch B2 is on, then the Vx2, general expression of Vx2 is equal to V reference by 2 into B2. Similarly, we will find what is the value of Vx1 and also Vx0. Suppose I want to now find what is the value of Vx1. Suppose if I want to find what is the value of Vx1 is only switch B1 is on and the remaining two switches are going to get off means we need to ground them. So therefore switch B0 is grounded and switch B2 is also grounded. But only switch B1 we are going to give to supply V reference. And then we are going to find this voltage. This voltage we are going to assume as Vx1. So this circuit we are going to get, this is a 2R grounded, this 2 is connected to V reference and this 2 is grounded and this is R and this is R. So I want to find what is this Vx1. So if you want to find this Vx1, very simple. So 2R parallel is overall value R plus R is again 2R. Then here we can see clearly. So now with the help of voltage division principle, so if you apply the voltage division principle, then finally we are going to get, so Vx1 is equal to V reference by 4. So V reference by 4 you are going to get. So we are going to get V reference by 4 is the answer we are going to get here. So now very important thing that you always need to understand, I want to find what is the general Vx1. General Vx1 is equal to V reference by 4 into B1. So whenever B1 is on, replace B1 is equal to 1. Whenever B1 is off means replace B1 is equal to 0. Then we are going to get this one because binary numbers either it can be 0 or either it can be 1. So this is a concept that you always need to keep in your mind. So finally I can say that the general expression of Vx1 is equal to V reference by 4 into B1. I want to find what is the value of Vx0. So Vx0 means I have already told you only switch B0 is on. But the switch B1 and B2 are off. So we are going to have the switch B1 and switch B2. Off means we should ground them. On means we have to connect to the reference voltage. So therefore switch B0 is connected to the reference voltage and switch B1 is referenced, it is grounded, and the switch B2 is also grounded. So this is the circuit that we are going to get. So now I want to find what is this voltage Vx0. See, this is a very simple network analysis problem. We can easily simplify this problem, that the network, and finally we can find the value of Vx0. So if we do like that, we are going to get Vx0 is equal to V reference by 8. So this is the voltage that we are going to get. So now I want to find what is the general expression of Vx0. General expression of Vx0 is equal to V reference by 8 into V0. So general expression of Vx0 is equal to V reference by 8 into V0, because whenever the switch B0 is on means V0 is equal to 1. If whenever the switch B0 is equal to off means replace B0 is equal to 0. So now what is the net voltage Vx? If all the switches are on, then what is the voltage Vx? If switch B0 is on, B1 is on and B2 is on. If all are on, then what is the voltage Vx? I have already told you Vx is equal to Vx2 plus Vx1 plus Vx0 with the help of superposition principle. So if all the switches are on, means they are going to be supplied to V reference. They are connected to V reference. The net voltage is the voltage due to only switch B2 is on, only voltage due to when switch B1 is on, only due to voltage because of switch B0 is on. So we have to do by the help of superposition principle. If we add each and everything, then we are going to get the net voltage Vx. So we know the value of Vx2, we know the value of Vx1, we know the value of Vx0. general expressions, substitute them and do the simplification, and finally we are going to get V reference by 8 into 4b2 plus 2b1 plus b0. So this is nothing but a decimal equivalent of binary input. Decimal equivalent of binary input. So So basically it is the binary input B0, B1, B2. So I want to convert it into decimal format. So you have to go for 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. You do the multiplication 4 into B2 plus 2 into B1 plus B0. It is nothing but decimal equivalent of this binary number. So this is the decimal equivalent of the binary input. So this is the decimal equivalent of the binary input. So finally I can say Vx is equal to V reference by 8 into decimal equivalent of the binary input. So generally I can write the general expression is equal to Vx is equal to V reference by 2 to the power of n into sigma I into 2 to the power of I into bi, or simply I can write which is Vx is equal to V reference by 2 to the power of n. N is nothing but number of binary inputs, into sigma means it is called as the decimal equivalent of this binary input. The decimal equivalent of this binary input. So this is V reference by 2 to the power of n into, this is the decimal equivalent of this binary input. So this is the point that you always need to keep in your mind. So what is the Vx? Vx is nothing but V reference by 2 to the power of n. So V reference by 2 to the power of n. N is nothing but number of binary bits. In this case we have binary bits 3. So n is equal to 3 minus 2 cube is equal to 8. So this is the expression that we are going to get. So then Vx is equal to V reference by 2 to the power of n into the decimal equivalent of this binary input. The decimal equivalent of this binary input. So Vx is equal to V reference by 2 to the power of n into the decimal equivalent of this binary input. So this is the important formula that you always need to remember. So here suppose if you want to find what is the Vx, let me assume for 101. Suppose here B2 is equal to 1 and B1 is equal to 0 and B0 is equal to 1. So for 101 I want to find what is the Vx. So then just substitute here, very simple. V reference by 2 to the power of n. N is nothing but number of steps are 3. So 2 cube into, just find the decimal equivalent of this number. So 101 means the decimal equivalent is equal to, very simple, which is 4 into 1 plus 1, which is nothing but 5. So therefore if you solve this one, V reference by 8 into 5, then we are going to get Vx. So listen carefully, this is always constant value. So this is always constant. No matter whatever the combination of B2, B1, B0, this is always constant. But only thing is, this is the variable that we are going to get. This is always constant, but this is only variable. So this is a point that you always need to keep in your mind. So Vx is equal to V reference by 2 to the power of n into decimal equivalent of this binary input. So this decimal equivalent can change. This decimal equivalent can change, but this value will be always constant because this is V reference by 2 to the power of n. N indicates number of binary switches. So like this, we have to do this value. We have to get the value of Vx. So now listen carefully. Suppose a small example I want to give you. Suppose this is the general expression I have already told you. So Vx is equal to V reference by 2 to the power of n into decimal equivalent of the binary input. Suppose I am going to take three switches B2, B1, B0. Suppose I am going to do the switching like this. B2 is equal to 0, B1 is equal to 1 and B0 is equal to 0. So I want to do the switching like this. Then I want to find what is the value of Vx. So Vx is equal to V reference by 2 to the power of the number of switches are 3. So 2 cube into the decimal equivalent of this number. What is the decimal equivalent of this number, which is 2? So 2. So if you solve this one, we are going to get V reference by 4. So this is the voltage that we are going to get across the Vx, which is V reference by 4. This we have already got in the previous case only. We have seen this value, which is for Vx1 we got V reference by 4. So this is the way that I want to tell you that no matter whatever the decimal equivalent, this value will be always constant. Only this decimal value is going to get changed, but this value is always constant for a fixed binary bits. Only the switching is going to get changed, 101 or 010 like that, but this value is always constant. So finally Vx is equal to V reference by 2 to the power of n into decimal equivalent of this binary number. See, I have already told you DAC is of two types. The types of DACs are the weighted resistor DAC and the R2R ladder type DAC. So just now we have seen the R2R ladder type DAC. But now we are going to see the weighted resistance digital to analog converter circuit. So this is called as the weighted resistor DAC, or simply we can say weighted resistor digital to analog converter circuit we are going to study in a very detailed manner. So this is a circuit that you always have to keep in your mind. See, I have already told you one important point. I think you have remembered in the DAC. When I am going to tell you about the formulas, I have already told you the resolution in case of R2R type of DAC is V reference by 2 to the power of n. I have told this important point. The resolution, the formula of the resolution for the R2R ladder type DAC is VR by 2 to the power of n. Yes, this is the value you are seeing right now in front of you. This is the formula which is the proof of this one. So we can say for R2R ladder type of DAC, basically we can say the resolution is equal to V reference by 2 to the power of n. So now we will go for the another type of DAC. This is the second type of DAC. Here, weighted resistance digital to analog converter circuit, or simply we can say this is also called as the weighted resistance DAC type circuit. So we can see clearly this is the circuit. So this is the circuit that you are going to see here. See, these are the resistance. Let me assume this is resistance R, this is a 2R, this is a 4R, this is 8R. Means it is doubling. This is R, 2R, 2R double is 4R, 4R is 8R. It is doubling each time. So R double is 2R, 2R doubling is 4R, 4R doubling is 8R. Next 8R doubling is 16R. Like that you have to double for each and time. Then this is all V reference voltage that we are going to apply. So this is the reference voltage that we are going to apply here. You can see clearly from this circuit itself, which is the reference voltage that we are going to get applied. So this is the switching. So these are the switches. This is the B0, B1, B2, B3. So this is called as the LSB and this is called as the MSB. Listen carefully. From up to down, the resistance increases. From up to down, the resistance decreases. But from down to up, the priority of bit increases. Means this is MSB and this is LSB. So listen carefully. The low resistance bit is always MSB and high resistance bit is always which is always LSB. So because you can see clearly, whatever the switch connected to low resistance is always MSB and the switch which is connected to high resistance is always LSB. So this is a point that you always need to keep in your mind. So therefore, as you move from up to down, the resistance decreases, and the switch which is connected to low resistance is always MSB, and the switch which is connected to high resistance is always LSB. So now I am going to connect like this. So this is B0, B1, B2, B3. I am going to take here 4 switches. So now this is a op amp. So this is basically an op amp. So now this is, see, let me assume the current in each one. Let me assume this current is I0, here I1, here I2, here I3. Then what is the overall current with the help of KCL? Let me assume this is some IF. As I already told you, in an op amp, because of huge amount of impedance, these currents are 0. So these currents are 0 means whatever this current should flow through here, because the current is equal to 0 ampere. So whatever this current should flow here, so therefore here also this IF. But I have also told you, by using the virtual short circuit concept, if this is 0 volt, then this is also 0 volt, because V plus is always equal to V minus. If this is 0 volt, then this is also 0 volt. So now we are going to apply some basic things in the op amp, and it is a negative feedback amplifier. So we are going to assume let 4 bits like V3, V2, V1, 0. So B0 is always LSB and B3 is always MSB. I already told you, whichever the switch connected to low resistance is always MSB, and the switch which is connected to high resistance is always LSB. So these points that you always have to keep in your mind. So this is MSB and this is LSB. So then what is the current I3? I3 is equal to, which is VR by R, voltage by, because this is 0 volt, right? So voltage difference is VR minus 0, which is VR by R. But we have to multiply general expression B3. So therefore I3 is equal to VR by R into B3. Whenever B3 is on, means B3 is equal to 1, then only current will flow. Otherwise current flow is 0. So if switch B3 is on, means B3 is equal to 1, then only current is going to get flow. Otherwise if B3 is off, means it is connected to ground but not to supply. So therefore current will become 0 there. So this is the point that you always have to keep in your mind. So I3 is equal to VR by R into B3. Similarly, what is I2? VR by 2R into B2. Similarly, what is I1? I1 is equal to VR by 4R into B1. Similarly, what is I0? I0 is equal to VR by 8R into B0. Because this voltage is 0, so voltage difference is always equal to VR. So I3 is equal to VR by R into B3, I2 is equal to VR by 2R into B2, and I1 is equal to VR by 4R into B1, and I0 is equal to VR by 8R into B0. So what is the net current IF? It is a current because of all these currents. So IF is equal to I3 plus I2 plus I1 plus I0. So if you do the addition of all these things, then I have already told you this is 0, this is V0. So what is the voltage difference? So 0 minus V0 is equal to IF into RF. So V0 is equal to minus IF into RF. So V0 is equal to minus RF into IF. So V0 is equal to minus RF into IF. So IF is nothing but you have to add all these things. Then if you multiply by RF, then keeping minus here, you are going to get the output voltage. So what is the LSB resistance? I have already told you what is the LSB resistance. LSB resistance means for the LSB switch, the resistance is nothing but 2 to the power of n minus 1 into MSB resistance. MSB resistance is a very important point that you always need to understand. So LSB resistance is equal to 2 to the power of n minus 1 into MSB resistance. See, in this case, the number of bits are 4. The number of bits are 4. So 2 to the power of 4 minus 1 is equal to 3. And what is the MSB resistance? I have already told you, MSB resistance is nothing but MSB resistance means for MSB switch, the resistance is R. So therefore, 2 to the power of 3 into R is nothing but 8R. So therefore, we can say this is the LSB resistance. So for LSB, the resistance is 8R. You can see clearly from here. So this is an important formula that you always need to understand. So therefore, LSB resistance is always equal to 2 to the power of n minus 1 into MSB resistance. So therefore, LSB resistance is always equal to 2 to the power of n minus 1 into MSB resistance. So you can see clearly here, I have already told you for LSB, we are going to get the maximum resistance, and for LSB, we are going to see For LSB, we are going to connect the maximum resistance, and for MSB, we are going to connect the low resistance. So LSB resistance is equal to the power of n minus 1 into MSB resistance. So MSB resistance in this case is R, and LSB resistance in this case is 8R. So general formula is equal to, so LSB resistance is equal to the power of n minus 1 into MSB resistance. So LSB resistance is always equal to the power of n minus 1 into MSB resistance. So this is a very important formula. Every time they are going to ask in the AE examination. So therefore we can say LSB resistance is equal to the power of n minus 1 into MSB resistance. So LSB resistance is equal to the power of n minus 1 into MSB resistance. I already told you one important point. See, LSB for maximum resistance we are going to connect the LSB switch, and for low resistance we are going to connect the maximum means MSB switch. So for low resistance we are going to connect the MSB switch, and for high resistance we are going to connect the LSB switch. So LSB resistance is equal to the power of n minus 1 into MSB resistance. So this is the important point that you always have to remember. So the resistance connected to MSB switch is R, and the resistance connected to LSB switch is 8R in this case. So general formula, LSB resistance is equal to the power of n minus 1 into MSB resistance. So now we are going to discuss about the R2R ladder tag. R2R ladder tag. See, I already told you R2R ladder tag just now we have seen, but now we see somewhat deeper in it. Means we are going to analyze something more about this one. R2R ladder tag. See, it is also here basically we are going to have two things in this, which is normal ladder, means non-inverting amplifier and inverting amplifier. So with the help of these two things we are going to get that, we are going to design this normal ladder, and the remaining thing is called as an inverted ladder. So these two, we are going to discuss these two circuits in this R2R ladder type DAC. Just now we have seen R2R ladder DAC, but we have just only given the some general expression. We have already told you Vx is equal to V reference by to the power of n into decimal equivalent of binary input. Just now we have seen. So now this is the somewhat deeper analysis of this R2R ladder type DAC circuit. So for this normal ladder, see, for the first case is called a normal ladder. We are going to design with the help of non-inverting amplifier as well as the inverting amplifier, and the next one is called as the inverted ladder. So these two things we are going to study. So I have already told you in the previous case only this is the R2R network. So for R2R network I have already told you here whatever the resistance, extra resistance 2R is there, right? For that just beside that whatever the switch there, that is called as the LSB. I have already told that is called as basically LSB. So now here this is basically binary input. So input is binary. So we are going to get Vx. Just now we have seen. So this expression just now I already told you Vx is nothing but simply Vx is equal to V reference by to the power of n into decimal equivalent of this binary input. Just now I already told you. So now this is called as the Vx. So now we are going to keep some amplifier. With the help of amplifier we are going to increase this gain. So what is V0 is equal to Vx into gain. So therefore V0 is equal to Vx into this amplifier gain, which is J. So V0 is equal to Vx into J. So this is the internal architecture of this R2R ladder type DAC. So up to now we have learned only up to this case we have learned, but we are going to give some extra amplifier in order to increase this voltage. So V0 is equal to J into Vx. I have already told you what is the value of Vx. Just now we have seen Vx is equal to V reference voltage by to the power of n into decimal equivalent of this binary input. See, this is always constant. I have already told you this value is always constant. Only this value is going to vary as per the switching that we are going to give. Suppose, then what is the value of V0? V0 is equal to Vx into G. So therefore, substitute in the place of Vx, substitute this expression, we are going to get finally V0 is equal to reference voltage by to the power of n into decimal equivalent of the binary input into gain. So VR by to the power of n, I have already told you this is called as the resolution. This is called the resolution of the R2R ladder type DAC. I have already told you this point. And this is the decimal equivalent of the binary input, and this is the gain of the amplifier. So therefore, the output voltage of R2R ladder type DAC is equal to resolution into decimal equivalent of the binary input into gain of the amplifier. So this is the overall output voltage that we are going to get for this R2R ladder type DAC circuit. So this is a general case. So now we are going to study this specific case also, which is the normal R2R ladder tag that this is basically non-inverting amplifier we are going to study. So this is the non-inverting amplifier. You can see clearly this is the non-inverting amplifier because we are going to give input to this non-inverting terminal. So this is called as a non-inverting amplifier. So you can see clearly. So this circuit just now we have seen, this circuit just now we have studied. What is this value of Vx? Just now I have already told you Vx is equal to V reference by 2 to the power of n into decimal equivalent of the binary input. So this is I have already told you. So this is extra 2R we are going to give. This is a 2R, 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 2R. The whatever the switch just near to this one is always called the LSB. So this is V0, V1, V2, V3. So we are going to keep a resistor of R, R, R in between this. In between this only we are going to keep the R, R, R. So that is the reason it is called as a R2R ladder type DAC. So whatever this extra resistance 2R, the nearby switch is always LSB and the farthest one is always MSB. So this is base 0, B1, B2, B3 and these are R, R, R. So we are going to find this voltage. This is called as a Vx. So Vx voltage I have already told you, which is V reference by 2 to the power of n into decimal equivalent of binary input. Then we have to multiply by some gain. So this is the non-inverting amplifier. So what is the gain? 1 plus Rf by R1. Then what is the output voltage? So output voltage is equal to, this is Vx. So this total is Vx and this is the gain of the amplifier. So P reference by 2 to the power of n into decimal equivalent of binary input into gain of the amplifier, which is 1 plus Rf by R1. So in this case we are using only 4 switches, means n should be equal to 4, means only 4 binary inputs. So if we substitute n is equal to 4, we are going to get the expression for this op amp, for this circuit we are going to get. So V0 is equal to resolution into decimal equivalent of binary input into gain of the op amp. So this is the output expression that we are going to get. So output voltage is equal to resolution into decimal equivalent of binary input into gain of the op amp. So therefore V reference by 2 to the power of n into the decimal equivalent of binary input into 1 plus Rf by R1. So this is the value that we are going to get finally. So the circuit is called as the 4-bit R2R ladder DAC using the non-inverting op amp. So you can see 4-bit R2R ladder type DAC which is using by non-inverting op amp. So therefore it is a 4-bit R2R ladder type DAC which is built using the non-inverting op amp. So now we learn about another case. See, I have already told you in the normal ladder there are two things, non-inverting amplifier and inverting amplifier. So this is called as non-inverting amplifier. So therefore now, see, whatever this we are going to give to some extra means non-inverting terminal. So this we are going to go to input terminal, inverting terminal. So this is called as the inverting amplifier. So this is the inverting amplifier. For this we are going to give to this circuit. This circuit just now we have studied. So this circuit just now we have studied, right? So we have studied this extra circuit. So this circuit just now we have studied. So therefore what I am trying to tell you, so what is the voltage Vx? Vx voltage just now we have seen. What is this voltage? See, Vx voltage is very simple, which is V reference by 2 to the power of n into decimal equivalent of the binary input. Decimal equivalent of binary input. I have already told you this voltage Vx is nothing but simply V reference by 2 to the power of n into decimal equivalent of binary input. And for 2R, for this 2R, the nearby switch is always LSB and the farthest is always MSB. So now very important point that you always need to understand. Here there is some extra resistance R1. So what is the gain of this one? So gain of this is nothing but minus Rf by R1. But listen carefully. If all the switches are on, then what is going to happen? If all the switches are on, then with the help of Thevenin theorem, I want to find what is the equivalent resistance. Equivalent resistance is nothing but 2R, which is R. R plus R, 2R. Again 2R will become R. R plus R, 2R. 2R will become R. R again 2R. 2R again R. So we are going to get the equivalent resistance across these terminals is nothing but which is R. So therefore simply we can say the overall input resistance is now going to become R plus R1. So this Thevenin circuit. Suppose if you want to find what is the Thevenin circuit of this equivalent circuit, the Thevenin circuit will have Thevenin voltage and Thevenin resistance. Thevenin voltage is nothing but Px, which is V difference by 2 to the power of n into decimal equivalent of binary input. And what is the Thevenin resistance? Thevenin resistance is very simply just like what I told you. The Thevenin resistance is always equal to R. It is always equal to, the Thevenin resistance is always equal to R. No matter whatever the switching that we are going to do, always it will be always equal to R, because see, whether you connect to supply or whether you connect to ground, if you want to find Thevenin voltage, definitely we are going to short circuit this voltage source. Always they are going to connect to ground. So therefore simply we can say, no matter whether you switch, whether you on the switch or whether you off the switch, always the Thevenin resistance is always equal to R, because if you want to find Thevenin resistance, always you have to do the short circuit of voltage source. Whether you short circuit the voltage source or whether you connect to voltage source or whether you not connect to voltage source, means whether you ground it, always the Thevenin resistance is always equal to R itself. So therefore simply we can say that the Thevenin resistance and Thevenin voltage we know, which is Thevenin voltage is equal to V difference by 2 to the power of n into sigma, the decimal equivalent of binary input, and the Thevenin resistance is R. So what is the overall input resistance? R plus R1. So therefore what is the overall gain? Gain is equal to now minus Rn by R plus R1. So we have to multiply this gain, then only we are going to get the overall output voltage. So therefore finally the output voltage is equal to the Vx is nothing but V difference by, the resolution is equal to V difference by 2 to the power of n into decimal equivalent is sigma, the decimal equivalent of binary input into gain is minus Rf by R plus R1. So then what is the output voltage? So suppose I wanted to tell you, this is input currents are always equal to 0. So this is also 0 volt. So whatever this current If should pass here. Suppose let me assume this is the current If in this R1. So the same current If should pass here also, because the current here is 0. So here it is If. So 0 minus V0 is equal to If into Rf. So V0 is equal to minus If into Rf. So if you want to find what is the value of If, then V0 value we know. So we equate these two equations. So if we equate these two equations, Rf cancels and minus cancels. So If is equal to V difference by 2 to the power of n into decimal equivalent of this binary input into 1 by R plus R1. So you are going to get this expression, because if you equate these two equations, two expressions, Rf cancels, minus cancels. So we are going to get this remaining term, which is the If is equal to V difference by 2 to the power of n into decimal equivalent of binary input into 1 by R plus R1. This is the current which is If is flowing in this feedback resistor. So this is the expression that you always have to keep in your mind, because in the examinations they are going to ask based on this concept. So this is the last concept regarding the R2R ladder DAC circuit, because in the normal ladder we have studied about the non-inverting amplifier as well as the inverting amplifier, and this is the last case which is called as the inverted ladder. So you can see clearly this is the 4-bit inverted ladder. So this is basically 4-bit inverted ladder. So now see, this is the circuit that we are going to see here. So this is the 4-bit inverted ladder. So this is the reference voltage I have already told you, and this is the 2R. So we are going to take here 4 bits, B0, B1, B2, B3. So here it is extra, with the extra resistor of 2R. Here 2R, R. So here this is whatever the switch which is corresponding to this extra resistance, which is called the LSB, and the further one is the MSB. So B0, B1, B2, B3. So now we are going to connect to these branches like this. So these are the branches, and we are going to go to the inverting amplifier. It is also inverting amplifier. It is also equal to inverting amplifier. So now if you listen carefully, one important point that you are going to get here. If you listen carefully, one important point I can tell you. So let me assume this current is I0, current is I1 here, current is I2, and current is I3. So now here let me assume this overall current is IF. As it is 0 volt, so here also it is 0 volt. With the help of virtual short circuit, the current inside them is always equal to 0. So whatever this current should flow here. So here it is IF means here also it is IF. Then here what is the value of I? So what is the value of I? So what is the value of I is nothing but, I have already told you, I is nothing but, see, I want to find what is the value of I. Listen carefully. I want to find what is the overall Thevenin resistance. Overall Thevenin resistance from here to here. I have already told you whether they are going to connect to ground, whether they are going to connect to here, or whether they are connected to this one. Any of this is 0 volt, whether the switch is connected to this voltage, this part, or whether the switch is connected to this one, always they are connected to ground, because this is a virtual short ground. and this is actual ground. So no matter whether they connect to here or whether they connect to here, always these lines are at the zero potential. So if you want to find what is the overall resistance, the Thevenin resistance is very simple. These two are in parallel. So R plus R, 2R. 2R parallel means R plus R in series means 2R. 2R again parallel, you are going to get R plus R again 2R. 2R again parallel means you are going to get R. So overall resistance is going to become now R only, because I have already told you whether they connect to this point or whether they connect to this point, always they are at the same ground potential, because with the help of virtual short circuit, if this is 0, this is also equal to 0. So overall resistance is always equal to R. So therefore, what is the input current I? I is equal to V reference minus 0 by overall resistance is R. So therefore, V reference by R you are going to get. So I is equal to V reference by R. So this is the current I. So it is going to divide into two parts. So I by 2, I by 2. Here so this I by 2 is again divided into two parts, I by 4 and I by 4. Again this current I by 4 is divided into two parts, I by 8 and I by 8. Again this current I by 8 is divided into two parts, again I by 16 and I by 16. So this is the current division. So this is I means I in two parts, I by 2, I by 2. Again it is divided into two parts, I by 4 and I by 4. Again it is divided into two parts, I by 8 and I by 8. Again it is going to be in two parts, I by 16 and I by 16. So this is the current division. Then what is the value of I0? I0 is nothing but, just now we have seen, I0 is nothing but, if you connect this switch to here, what is I0? I0 is equal to, which is I by 16 into B0. If B0 is equal to 1 means you are connected to here, then I by 16. If you are not connecting means I0 is equal to 0, because B0 is equal to 0. If B0 is equal to 1, we are going to get I by 16. If B0 is equal to 0, we are not going to get any current means 0, because whenever B0 is equal to 1 means we are connecting here. Whenever B0 is equal to 0 means we are connecting here. So therefore, the general expression of I0 is equal to I by 16 into B0. Similarly, what is the expression of I1? I1 is equal to I by 8 into B1. So I2 is equal to I by 4 into B2. And I3 is equal to I by 2 into B3. So this is the general expression of this one. So whenever the switch is on means they are 1. If the off means 0. 1 means they are connecting to this terminal. Off means they are connecting to this ground. So I already told you what is the value of I0. I0 is nothing but, which is I by 16 into B0. I1 is equal to I by 8 into B1. And I2 is equal to I by 4 into B2. And I3 is equal to I by 2 into B3. Now I already told you I0 is equal to I by 16 into B0. And I1 is equal to I by 8 into B1. And I2 is equal to I by 4 into B2. And I3 is equal to I by 2 into B3. But what is the value of I? I is equal to V reference by R. So substitute here we are going to get finally I0 is equal to V reference by 16R into B0, and I1 is equal to V reference by 8R into B1, and I2 is equal to V reference by 4R into B2, and I3 is equal to V reference by 2R into B3. I have already told you what is the value of IF. IF is nothing but summation of all the currents with the help of KCL. So IF is equal to I0 plus I1 plus I2 plus I3. So if we do the summation of all these currents, then we are going to get finally, which is IF is equal to V reference by 16 into 8B3 plus 4B2 plus 2B1 plus B0 into 1 by R. Then we can see what is the value of IF. The general expression is nothing but IF is equal to V reference by 2 to the power of n into decimal equivalent of this binary number into 1 by R. So this is the expression that you are going to get. The IF is equal to V reference by 2 to the power of n into the decimal equivalent of the binary input into 1 by R. But what is V0? Just now we have seen what is V0. V0 is nothing but, just now I have seen, told you 0 minus V0 is equal to IF into RF. So V0 is equal to minus IF into RF. So we know the value of IF. Substitute here. Then we are going to get the expression V0 is equal to here. So V reference by 2 to the power of n into decimal equal to the binary input into minus RF by R. So this is the expression that we are going to get, output voltage. So V0 is equal to V reference by 2 to the power of n into decimal equivalent of binary input into minus RF by R. So this is called as the resolution, and this is called the decimal equivalent of the binary input, and this is called as the gain of a inverting amplifier. So therefore, V0 is equal to product of the resolution in decimal equal of binary input into gain of the amplifier. It is an inverting amplifier, so therefore the gain is minus Rf by R. So this is a point that you always have to keep in your mind. So we have successfully completed all the things regarding the DAC. So regarding the digital to analog converter, we have studied each and everything. But now we will study about the ADCs. All the ADCs now we are going to study in a very detailed manner. So I have already told you easily to remember the sequence, which is captain searching first the code. Means C means counter type, S means SAR type, F means flash type, and D means dual slope. So all these ADCs now we are going to study. So successfully we have completed all that digital analog converter, but now we are going to study about the ADCs. So the first thing is we are going to study about the counter type ADC. Counter type ADC is also called as the ramp type ADC. So counter type ADC is also called as the ramp type ADC. So basically we are converting the analog input to the binary output. So we are converting the analog input to corresponding binary output. So for this corresponding analog input, we are going to convert the corresponding binary output. We are going to see how we are going to make it. So you can see this is the circuit diagram of a counter type ADC or RAM type ADC. So this is the op amp that we are going to consider. It's a positive and negative. So we can see it's a we are giving input to plus terminal, means it is a non-inverting op amp. So therefore this is the plus reference and 0 voltage that we are going to give. And here we are going to keep a AND gate. Here the output of the op amp is given as the one input of the AND gate, and the other input of AND gate we are going to give a clock signal. And this output of this AND gate we are going to give to up counter. Up counter means it is going to read from 0 0 0 0 0 0 1 0 0 0 and 2, means it is going to increase the count from 0 1 2 3 like that. It is going to increase the count. So this bit we are going to consider this as the LSB, and this bit we are going to consider this as the MSB. So basically this is called as the binary output. So whatever this is called as the binary output. So now what we are going to do, whatever this digital output is there, right? So we are going to convert into corresponding analog voltage with the help of this DAC. So whatever this binary output that we are going to get here, we are going to convert into corresponding analog voltage, which is V0 DAC is also called as the analog voltage, because DAC is going to convert the binary input to we can say analog voltage. So we are going to compare these two voltages. We are going to compare these two voltages. So this op amp is going to compare these two voltages, and whenever if you compare these two voltages, you can see clearly it is going to compare these two voltages, and then we are going to get this result. If suppose if VA is greater than this voltage, then we are going to get plus reference. If VA is less than this value, then we are going to get 0 voltage, because if this voltage is greater than this voltage, we are going to get output as plus V reference. Otherwise, if this voltage is less than this voltage, then we are going to get, here we are going to get 0, because this is a 0 voltage. So whenever this is 0, everything is going to become 0. So the counter is going to stop its clocking. So we are going to get the final steady state. So therefore final steady state we can easily read from seeing this counter. So finally what I am trying to tell you very simply, this counter is an up counter. It is always reading from 0 1 2 like that. It is going to give you the binary format of this equivalent. It is going to give you the binary equivalent of this analog input voltage. We don't know what is the analog input voltage. We don't know its exact value. So we are trying to figure out with the help of this circuit. So we are trying to figure out this. We are trying to figure out what is the exact value of this voltage with the help of this circuit by seeing this up counter result. It is a binary format, and we try to convert it into decimal format, and we'll try to check whether it is same or not. But there will be a small amount of error. No matter how much you do, always there will be a small amount of error also you are going to get. So this is the thing. This is the simple circuit. So always this is acting like a open op amp, because we are not going to give any feedback. This is basically acting like a open loop op amp. So whenever this voltage is greater than this voltage, we are going to get here plus V reference. Whenever this voltage is greater than this voltage, we are going to get 0 voltage. Whenever this voltage is slightly greater than this voltage, it is going to become 0. So this counter is going to stop its counting. So therefore, from seeing that, we know what is the binary format of this corresponding analog voltage. It may be small, this value, decimal format will be small amount of greater when compared to this value, but it is approximately equal. So therefore, simply we can say this is the binary binary output we are going to get. This is the LSB and this is the EMSB. So inside we are going to use the DAC. Just now we have seen different types of DACs. You can use any one that we have studied up to now, and we can simply analyze the circuit. Then what is the V0 DAC? Just now we have seen the output voltage of DAC. Just now we have known, which is V0 DAC is nothing but it is the product of the resolution into the decimal equivalent of the binary, the decimal equivalent of the value present in the up counter. So whatever this value present in the up counter, the decimal format you have to listen into gain of this op amp. Suppose if there is any gain, if there is any op amp inside this DAC, you have to multiply by gain. If there is no gain, if there is no op amp means you have to multiply by 1. If there is any op amp inside this DAC means you have to multiply by its corresponding gain. So what is V0 DAC is nothing but it is a product of the resolution into decimal equivalent of this. Decimal equivalent of this the value present in this up counter into gain of the op amp. If any op amp is present inside this DAC means you have to multiply by corresponding gain. Let we are going to assume, and we are going to generally assume that gain is equal to 1 and also resolution is equal to 1. So we are going to generally assume that the gain of the op amp inside this DAC is equal to 1 and the resolution of this DAC is nothing. But we are going to, for easier purpose, we are going to assume this 1. Then what is the error? Error is nothing but, so error between them. So what is that? This is the actual value and this is the value that we are going to get with help of DAC. So error is nothing but the difference between these two things. So error is equal to mod of the V0 DAC minus VA. So the VA is the value and the voltage that we really want to measure, but this is the voltage that we are going to get with the help of DAC. So we are going to take this modulus of this one. So error is nothing but the modulus of V0 DAC minus VA will be less than the resolution at steady state. It will be always lesser. The error will be very lesser when compared to the resolution. So it will be always lesser when compared to the resolution of this DAC. So therefore it will be lesser than the resolution at the steady state. So whatever this error value will be very small. It will be very lesser than compared to resolution of this DAC. So it is at a steady state we can say the error is always lesser than the resolution of this DAC. So therefore error is equal to modulus of V0 DAC minus VA will be lesser than the resolution at the steady state of the DAC. So what is the value of VA? I have already told you VA should be always less than or equal to maximum decimal equivalent of up counter. Yes, see, always VA should be always less than or equal to maximum decimal equivalent of up counter. So more than that it cannot be. So if it is more than that, what is going to happen? If it is more than that, what is going to happen? Very simple. If VA is greater than the maximum decimal equivalent of up counter means here, then this value will be always lesser than the VA. So output of op amp, will be always plus V reference. So therefore you cannot get the result. So therefore always VA should be always less than or equal to the maximum decimal equivalent of op amp. Then only we can get this V0 DAC is greater than VA is possible. Then only we are going to get the output of op amp as 0. Then the counter is going to stop its counting. Otherwise the counter will always do the counting from 0 to highest value. Again it go back and it is doing its repetition in a loop manner. So therefore always the analog voltage should be always less than or equal to maximum decimal equivalent of the up counter. See generally we can also see like this. VA should be always less than or equal to this V0 DAC. So V0 DAC. So what is the maximum value? The maximum value of V0 DAC should be always greater than the VA. Or simply we can say even like that also. So therefore here I have already assumed resolution is equal to 1 and the gain is equal to 1. So because of that reason only I am going to tell you V0 DAC is equal to decimal equivalent of value present in up counter. If these are not equal to 1 means definitely VA should be less than or equal to the maximum value of the V0 DAC. Or simply if you are going to assume gain is equal to 1 and resolution is equal to 1, then the maximum value of DAC is nothing but the maximum value of the decimal equivalent of the value present in the up counter. So therefore finally we can say that VA, so in the general format we can say that VA should be always less than or equal to maximum value of the output voltage of the DAC. Then only the counter is going to get stopped after some time, and then we can read from the counter what is the binary equivalent of this analog voltage. Approximate value we can see. Even there will be a small error, the error is always lesser than the resolution of the DAC itself. So in n-bit counter type ADC, the maximum value, the maximum number of clock pulses it can count is, which is to the power of n minus 1, because in a n-bit counter type ADC, the maximum number of clock pulses it can read is equal to the power of n minus 1, because I have already told you here, this is a n-bit, right? N-bit means the maximum decimal equivalent we can get to the power of n minus 1. So because if there are n bits, the binary inputs, the binary outputs are 4, suppose n bits. So with the help of n bits, the maximum number of clock pulses we can get is to the power of n minus 1. So therefore, this to the power of n minus 1. So within this, it should read that value. So within this to the power of n minus 1, it must read its corresponding analog voltage VA. So therefore, here we can say within this clock signal, within this clock time, it should read what is the corresponding binary input of this analog voltage. It should read its value. So therefore, in a n-bit counter type ADC, the maximum number of clock pulses it can count is to the power of n minus 1. So this is the maximum. See, sometimes it can read even lesser than this one, but what is the maximum value? So the maximum value is to the power of n minus 1. So this many number of clock pulses, within this many number of clock pulses, it should read that VA. It should read the VA in the format of binary format. So therefore, in n-bit counter type ADC, the maximum number of clock pulses it can count is to the power of n minus 1. So in a n-bit counter type ADC, the maximum number of clock pulses it can count is to the power of n minus 1. So the maximum conversion time, so clock pulses we know, just multiply by t clock, we are going to get maximum conversion time is nothing but to the power of n minus 1 into t clock. So within this time, it should read its value analog voltage in terms of corresponding binary output. And the minimum conversion time is what? T clock. So minimum is nothing but t clock within 1 clock. Suppose minimum time is within 1 t clock, it can read what is the value of the VA. It can read its value in the VA in the format of binary input. So this is the minimum time clock and this is the maximum t clock. So maximum conversion time is to the power of n minus 1 into t clock, and minimum conversion time is t clock. So you can see clearly this conversion time is depending upon the input voltage. You can see clearly this conversion time is depending upon the input voltage. As the input voltage increases, the conversion time, the actual conversion time is also increases. As the input voltage decreases, the actual conversion time will also decreases. So we can say finally that very simple. This conversion time is depending upon the number of bits and also on it is also depending upon the input voltage. So that is the reason I already told you this conversion time is going to depend on the input voltage and also on the number of bits. So therefore it can read maximum time, the maximum conversion time is to the power of n minus 1 t clock, and the minimum conversion time is only t clock. So we can say as the input voltage increases, the actual conversion time is also increases. As the input voltage decreases, the actual conversion time is also decreases. So what is the average number of clock pulses? Just do the average of these two values we are going to get. So therefore, to the power of n minus 1 plus 1 by 2 is nothing but to the power of n minus 1 we are going to get. Plus and minus 1 cancels, so we are going to get to the power of n minus 1. So this average number of clock pulses we are going to get. So within this average number of clock pulses we are going to detect the output. We are going to detect the analog input. So this is called as the average number of clock pulses, which is equal to the power of n minus 1. So therefore finally we can say that very simple, the maximum conversion time is equal to the power of n minus 1 into t clock, and the minimum conversion time is equal to t clock. So average number of clock pulses is equal to the power of n minus 1 plus 1 by 2 is nothing but plus and minus 1 cancels, we are going to get to the power of n minus 1. So to the power of n minus 1. So these are the average number of clock pulses required in order to detect the analog input voltage. So this is a very important point, and finally I can say very important point, which is the conversion time is going to depend upon the number of bits and also on the input voltage. As the input voltage increases, the conversion time increases. As the input voltage decreases, the conversion time will decrease. These are the maximum values. These are the maximum and the average values. So we can say clearly here, in counter type ADC or RAM type ADC, conversion time varies with input voltage in the input voltage and analog voltage. If input voltage is more, then the wait for more time to get the output. And already I told you one important point in a conversion time ADC, if the analog input voltage increases, you have to wait for more time to get the result through the binary output. So if the input voltage is less means you will get the result, the binary output within a less number of time. If the input voltage increases means you have to wait for more amount of time. So therefore we can say the conversion time is going to depend upon the number of bits and also on the input voltage. So therefore we can say in commutator type ADC, the conversion time varies with input voltage. Input voltage. If input voltage is more, then wait for more time to get the output. That is what I am trying to tell you. So V0 DAC. So V0 DAC is nothing but the output voltage of DAC with respect to time. So it will be for certain time, it will be like 0, 1, 2, 3, 4, 5. Because I already told you, I am going to assume the gain is equal to 1 and resolution is equal to 1. So whatever V0 DAC is equal to decimal equivalent of binary input. So for the corresponding binary input, we are going to get decimal values like 0, 1, 2, 3, 4, 5. So like this, we are going to get at a certain value, at a certain instant, we have what the V0 DAC is greater than actual value of VA at that instant. The output voltage of op amp is going to become 0. So the counter is going to get stopped. So therefore we are going to see that result and we are going to approximate it. It is not nearly equivalent to the actual value of the analog voltage. With the help of this, we are going to get this one. So therefore, let VA is equal to 4.7. Suppose I am going to assume VA is equal to 4.7. Then you can see clearly VA is 4.7 is here. So therefore, what we are going to get, V0 DAC is going to get here 5 volt. Then only if V0 DAC is equal to 5 volt, then only we are going to get the op amp output is equal to 0. So counter is going to get stopped. So therefore 5 volt is nothing but 0.0101 in the binary output that we are going to get. I have already told you I am going to assume the gain is equal to 1 and the resolution is equal to 1. Then V0 DAC is equal to decimal equivalent of binary input, which is equal to 5 volt. 5 volt means 0101 is going basically on the up counter. So from seeing that, I am going to tell you that this is the binary format of this analog voltage. But actually you can see clearly there is a small amount of difference, right? A small amount of difference is going to present between the actual voltage and the voltage that we are going to get from the up counter. So this is the conversion. A small amount of error. This error is always lesser than the resolution of the DAC itself. The resolution of DAC is nothing but we are going to assume here 1. So this difference is equal to 5 minus 4, 4.7 is equal to 0.3. So 0.3 is always lesser than the resolution. Resolution is equal to 1. We have already assumed. So this error is always lesser than the resolution itself. So this is the point that you always have to keep in your mind. A small amount of error is present, but that error is always lesser than the resolution. So this is all about the counter type DAC, or is also called counter type ADC or RAM type ADC. One important point that you always have to understand that as the input increases, as the input analog voltage increases, the conversion time is also increases. But the maximum number of clock pulses are to the power of n minus 1 into t clock. The maximum conversion time is to the power of n minus 1 into t clock, and the minimum conversion time is t clock. So what is the average, which is to the power of n minus 1 into t clock. So this is the average number of clock, this average number of time conversion is required. But actually it is going to, as the input increases, the actual conversion time increases. As the input voltage decreases, the actual conversion time decreases. So whenever V0 DAC is greater than VA, then only the op amp will be zero voltage. Output of op amp is 0. Then only the counter is going to get stopped. So this is a point that you always have to keep in your mind. So we are going to discuss about the successful approximation register type ADC. So SCR, basically SCR is nothing but, SAR means successive approximation register. SAR means successive approximation register type ADC. Now we are going to study. So you can see clearly from this diagram. So from this diagram you are able to see clearly which is there is a op amp. Op amp is basically open loop, or we can say open loop op amp is there. So for the positive terminal we are going to give you an analog voltage of VA, and this is the plus VCC, and which is ground potential. So the output of this open loop op amp we are going to give to control circuit. So through this control circuit, if you see clearly, through this control circuit we are going to give the control circuit output we are going to give to SAR. SAR is called as the which is basically ADC. So this is the ADC that we are going to use. This is called as the SAR, successful approximation register ADC we are going to see here. So it is going to have SOC, EOC and clock frequency F. So it is going to have inputs like SOC, EOC and the clock frequency is F. So we can see clearly here this ADC is going to convert this analog voltage into some binary voltage. So binary output. So you can see clearly this is called as the binary output. So this is basically called as the binary output. So now whatever this binary output I want to convert into corresponding analog voltage to convert to this op amp. So I am going to use this DAC. So DAC is going to give you an analog voltage with respect to this digital output, or we can say digital input. So for this DAC is going to convert this corresponding binary input to corresponding analog voltage. These things I have already told you. So therefore it is going to compare this one. So whenever VA is greater than this voltage, then the output is plus VCC. Whenever this voltage is greater than VA, the output voltage is 0. So therefore it is going to stop the process. Same thing here also. SOC is called as the start of command. So SOC is called as the start of command. See, SAR has ring type counter. So basically this SAR is going to have the ring type counter and waves from high level to low level. So basically this is like a taraj. So we are going to we are going to weigh the from high level to low level. Means from high level to low level we are going to go in this process. See, it is basically like a taraj. If you go to any taraj shop, if you want to measure anything, first they will keep the high things of whatever the things they have, they will keep everything, and from that they are going to remove one after the another bar. So therefore they are going to match whatever two things are going to say in a balance them into two sides. So they are in one side they are going to keep so many things, in the other thing they are going to keep the particular thing to weight. So slowly they are going to remove the things. So therefore they are going to balance both of them. That is from, so add weights from high level to low level. Maximum number of clock pulses is equal to n. N is called as the number of bits of the SAR. The maximum number of clock pulses in order to detect this analog input is equal to n. So maximum conversion time is n into t clock. And the conversion time is independent of analog input voltage. I already told you for successive approximation, for successive approximation register, the whatever this conversion time is independent of the analog input voltage. So it is independent of the analog input voltage. So within this time you are going to get the result. So conversion time is independent of the analog input voltage. So conversion time is independent of the analog input voltage. The circuit is faster than the counter type ADC because you see clearly here n into t clock is very lesser when compared to the power of n minus 1 into t clock. So better than that, this is very fast. So you are going to get the result very fast when compared to previous one. So the circuit is faster than the counter type ADC. This is similar to Taraj in shops. I have already told you Taraj means weighing balance machine. So it is similar to Taraj in the shops. The conversion time for an analog signal sample to be converted to digital equivalent value is equal to n into t clock. I have already told you if you want to convert any analog signal into corresponding digital equivalent, the time taken is n into t clock. These things I have already told you in case of the SAR. So the conversion time for an analog signal sample to convert it into digital equivalent value is equal to n into t clock. It is depending only on the number of bits of binary input, but it is independent of the input voltage, no matter what are the input voltage. So within this time we are going to get the result. So therefore, but there will be a small amount of error is going to present always. Without error there is nothing like, you will always get a error. No matter how much perfect you try to become, always there will be some small amount of error. So SOC is called as the start of command, and SAR has basically ring type counter, and we have to add the weights from high level to the low level. And the maximum number of clock pulses is equal to n bit SAR. So within this the number of maximum pulses we are going to get the output. So therefore the maximum conversion time is n into t clock, and the conversion time is independent of the analog input voltage. So within this is a maximum conversion time. You can get in within this time also, but maximum this is n into t clock. So conversion time is independent of the analog input voltage, and the circuit is faster than the counter type ADC because we say n into t clock is lesser than the previous total time to get the result. So the circuit is faster than the counter type ADC. This is similar to Taraj in shops, and the conversion time for an analog signal sample to be converted into digital equivalent value is equal to n into t clock. So these are the points that you always have to keep in your mind regarding this SAR type ADC. So this formula is very much important because in the examinations they are going to ask regarding this questions based on this formula, which is n into t clock. So this is the circuit diagram of a SAR type ADC, which is an open loop amp. This is analog voltage I want to measure. So I am going to give it to this positive terminal. Then here, this is a plus VC and 0. This is a control circuit. So this is a SAR ADC. We are going to have SOC is called as the start off command. There will be some UC and the clock frequency F. So based on this, we are going to get the digital binary output. So within then we are going to have a here n-bit binary output. Here we are going to have the DAC. So it is going to convert the digital input to binary to analog output. So we are going to compare these two things. Whenever this voltage is greater than this voltage, so this output will be 0. So we are going to start the process. So this is the meaning of this circuit. So basically we are doing the comparison. So by comparing only we are going to get the result of the what is the value of this VA with the help of this circuit we are going to figure out. So SOC is called the start off command, and SAR as basically ring type counter, and we have to add the weights from high level to low level, and the maximum number of clock pulses is n. It is for n-bit SAR, and the maximum conversion time to get the value of the input and analog voltage in terms of digital equivalent value, which is n into t clock, and the conversion time is independent of the analog input voltage. The circuit is faster than the counter type ADC. This is similar to Taraj in shops, and the conversion time for an analog signal sample to be converted to digital equivalent value is n into t clock. So these things already I have explained. So now we are going to study about the flash type ADC. Flash type ADC means this is the fastest ADC, means within a small amount of time we are going to get the result. So this is called as the fastest type ADC. Easy way to remember is here there is a F here. So F means very fastest because the time conversion is very less. Within 1 t clock only we are going to get the result. No matter whatever the input voltage, we are going to get the result within this t clock only. 1 t clock only. That is the reason it is said to be fastest ADC. In n-bit conversion, minimum number of comparators is equal to, in n-bit conversion, minimum number of comparators which are required is to the power of n minus 1. So this is an important formula that you always have to remember. The number of converters required for n-bit conversion of this flash is nothing but to the power of n minus 1. So in n-bit conversion, the minimum number of converters required is to the power of n minus 1. So also called as a parallel type ADC, this flash type ADC is also called as a parallel type ADC. And the minimum number of resistors to provide reference voltage is equal to the power of n. So the minimum number of resistors to provide the reference voltage is equal to the power of n. And there is a priority encoder is used to provide the corresponding binary output, which is to the power of n cross n. So to the power of n cross n. I already told you encoder means it is going to convert any other number system to binary, whereas decoder is going to convert the binary number system to any other number system. So encoder is going to have to the power of n cross n. So to the power of n cross n you are going to get. I already told you the inverse of decoder is encoder. So for decoder we are going to get n cross to the power of n. So we will be reverse to the power of n cross n you are going to get here. So to the power of n input lines and n output lines. So this is our priority encoder, and the maximum conversion time already I have already told you it is t clock. So these are the important points that you always have to keep in your mind. So flash type ADC is also called as the parallel type ADC, and it is a very fastest ADC. And for the n-bit conversion, the minimum number of computers that we are going to require is to the power of n minus 1. And it is also called the parallel type ADC, and the minimum number of resistors to provide the reference voltage is equal to 4 to the power of n, and a priority encoder we are going to use to provide the binary output voltage for the corresponding this one. It is having a 2 to the power of n cross n priority encoder, and the maximum conversion time is equal to T clock. So within this T clock only we are going to convert the analog input voltage to the corresponding digital output. So these are the points that you always have to keep in your mind. So flash type ADC is always, it is a very fastest ADC because it has the minimum time conversion when compared to other ADCs. That is the reason it is said to be a fastest ADC. In the n-bit conversion, the minimum number of computers required is 2 to the power of n minus 1. It is also called as a parallel type ADC, and the minimum number of resistors to provide the reference voltage is 2 to the power of n, and there is a priority encoder is used to provide the binary output, which is having a 2 to the power of n cross n, because 2 to the power of n are the input lines and n are the output lines. Priority encoder. So encoder means I have already told you it is going to convert the any other number system to binary number system, and the maximum conversion time, in this you are going to get the result, which is T clock. So within this T clock we are going to get the output, means we can say that the binary output equivalent to the corresponding analog input voltage. So now we will see about the 3-bit flash type ADC. So 3-bit flash type ADC means the number of resistors required to provide the reference voltage is nothing but 2 cube, means 8 resistors are required, and the number of computers are 2 to the power of 3 minus 1 means 8 minus 1 is equal to 7 computers. So 8 resistors we are going to require to provide the reference voltage, and 7 computers are being required. So now we will see the diagram regarding this one. So you can see clearly, this is a picture that you can see clearly from this one. So this is a 3-bit flash type ADC. So this is a 3-bit flash type ADC diagram. So you can see clearly, I already told you here we are going to use 8 resistors to provide the reference voltage. So 1, 2, 3, 4, 5, 6, 7, 8. So 8 resistors we are going to keep here. So therefore now each having a all are equal resistors of R. So voltage drop across each and everything is same. So each is having a voltage drop of V by 8. So this is V by 8. So what is this? V by R plus V by 8 is 2V by 8, and here it is 3V by 8. So this voltage is nothing but from this point to ground. We are asking that these voltages are with respect to the corresponding node and the ground. If this is V by 8, then this is 2V by 8, this is 3V by 8, this is 4V by 8, this is 5V by 8, this is 6V by 8, and this is 7V by 8. So these are the voltages with respect to these nodes, with respect to the reference, we can say with respect to this reference of node potential or with ground potential. So the number of resistors required are 2 to the power of n. You can see clear here. So this is the supply, this is the reference voltage that we are going to apply. So this is the analog voltage that we want to figure out through this corresponding binary equivalent. I want to figure out then this is basically an analog voltage VA. We do not its value, we do need to figure out. So we are going to keep here 7 computers because 2 cube minus 1 is equal to 7 computers. So you can say clearly 1, 2, 3, 4, 5, 6 and 7. So we are going to take this one. So whatever this we are going to take to the negative terminal of the op amp. So we are going to keep this to the inverting terminal of the op amp. So all these nodes we are going to take to the inverting terminal of the op amp. So all these nodes we are going to take to the inverting terminal of the op amp. So you see clearly. So all these nodes we are going to take to the inverting terminal of the op amp. So now the remaining positive terminal we are going to give to the unknown analog voltage. So this analog voltage is given for all the positive terminals of the op amp. You can see clearly for all the positive terminals of the op amp we are going to give this VA. So now this is basically operating in the open loop. So this is operating in the open loop. So now we are going to provide a priority encoder. Priority encoder means 2 to the power of n cross n, as n is equal to 3. So 2 cube is equal to 8 cross 3. So this is 8 cross 3. Inputs are 8 and outputs are 3. So this is priority encoder. So therefore we are having 8. You can see clearly this is 1, 2, 3, 4, 5, 6, 7, 8. Total 8 inputs means I can write like this 0, 1, 2, 3, 4, 5, 6, 7. So by default I am going to make this pin as 1. So by default I am going to make this pin as 1. From 1 I am going to connect to this comparators. So C1, C2, C3, C4, C5, C6, C7, and then I am going to get the corresponding digital output. Always encoder is going to convert any other number system to corresponding binary number system. So these are the Y0, Y1 and Y2. So this is MSB and this is the LSB. So now we will discuss how the graph is going to, how the outputs are going to get for the corresponding VA. So what is the resolution? Resolution is equal to step size is equal to B reference by 2 to the power of n. So this is the formula that you always have to remember for the flash type ADC. For the flash type ADC, resolution is equal to step size is equal to B reference by 2 to the power of n. So 2 to the power of n, because n is nothing but n is equal to 3. So 3 is nothing but B reference by 2 to the power of 3 is equal to 8. So this is the minimum voltage it can detect, because you can see for each individual resistor what is the voltage, which is V by 8 here. So this is the minimum voltage. This is the minimum voltage it can measure. So this is the minimum voltage it can measure, means accurately this much amount of voltage it can measure. So this is the minimum voltage. Below this it can't measure. So above this only it can measure, but not below this one. So what is the resolution? It is V by 8 here. In this case means V reference by 2 to the power of n. So therefore, as there are 3 bits, so 2 cube is equal to 8. So V reference by 8. So therefore, what I am trying to say is, so what is the voltage drop across the individual resistor is V by 8. So above that voltage only it can measure, but not below that one. If any input voltage is lesser than V by 8, then it cannot measure. It should be always greater than V by 8. So therefore, the minimum voltage, or we can say resolution of the step size is V reference by 2 to the power of n, where n is called as the number of bits. So now we will see what is the table we are going to get. So you can see clearly this is the range of the analog voltage. This is the range of the analog voltage, and these are the comparator outputs, and this is the binary outputs. So we are drawing the table corresponding to these 3 things, very important. If the range of the analog voltage, unknown voltage that we want to figure out, and the comparator outputs, and also the binary outputs. So you can see clearly, suppose the minimum voltage is V by 8. Suppose if the analog voltage is lesser than V by 8, then what is going to happen? If VA is lesser than V by 8 means, simply we can say this is lesser than this value, means negative, and the inverting terminal is greater than the positive terminal. So what is going to happen? I have already told you, whenever this is happening, the output voltage is 0. So for all these things you are going to get 0, because I have already told you this voltage is lesser. The positive terminal voltage is lesser than the corresponding negative voltage. So for all the comparators, we can say clearly the negative voltage is greater than the positive voltage. So you are going to get the 0 output. So comparator outputs are all 0. So all these are 0. All these are 0. So all these are 0 you are going to get. So what is the binary output? So binary output means, see, if all these are 0 means this is activated. If this is activated means 0 is activated. What is the corresponding binary output for 0? It is 0, 0, 0. So 0, 0, 0. That is the reason we are going to keep always 1 for this 0, because here when all these are not activated, this will be activated. So therefore we are going to get the corresponding 0, 0, 0. So now suppose if VA lies between V by 8 to 2V by 8, then what is going to happen? Only this comparator is going to become active, while all the other comparators are going to become inactive, because here only for this one positive terminal voltage is greater than negative terminal voltage, whereas for the remaining comparators negative terminal voltage is greater than positive terminal voltage. So therefore all these values are 0, but here this is high, because positive terminal voltage is greater than the negative terminal voltage. So this is high. So therefore I have already told you it is a priority encoder. Priority encoder means, I have already told you, whichever the number which is high, if it is activated that one, that output only we are going to get. So listen carefully, here 0 is activated and 1 is also activated, but out of 0 and 1, which is more priority? 1 is more priority when compared to 0. So therefore the corresponding binary output we are going to get. So 1 is activated means, for 1, what is the binary output? 0, 0, 1. So 0, 0, 1 we are going to get. Only comparator 1 has the high active, and the remaining everything is 0. Similarly, if VA lies between 2V by 8 to 3V by 8, then what is going to happen? If VA lies between 2V by 8 to 3V by 8, then C1 is activated, C2 is activated, and the remaining things are going to become inactive. So therefore, the output of C1 is 1 and the output of C2 is 1. Both are going to get activated, and 0 is also activated. Out of these, 2 is having the more priority when compared to 0 and 1. So corresponding to 2, we are going to get the binary output, which is 0, 1, 0. Similarly, if VA lies between 3V by 8 to 4V by 8, if VA lies between 3V by 8 to 4V by 8, then we can say 1, 2, 3. All these three computers are going to become active, but not the remaining things. So these voltages are always high and these are 0. So you are going to get like this. Up to C3 you are going to get activated, but not this one. Out of this, C3 is having high priority when compared to other thing. So therefore, for the 3, the corresponding binary output is 0, 1, 1 we are going to get. Similarly, whenever the VA lies between 4V by 8 to 5V by 8, then up to C4, C1, C2, C3, C4 are being activated, but not the remaining 3. So out of this, these outputs are 1, but not this one. So out of this, only 4 is having higher priority. So corresponding to 4, you are going to get the binary output. So you can see 1, 0, 0. Similarly, if VA lies between 5V by 8 to 6V by 8, then up to C5, you are going to get output as 1 and these are 0. So therefore, out of 5 is having more priority when compared to other. So therefore, corresponding to 5, you are going to get the binary output, which is 1, 0, 1. Similarly, if VA lies between 6V by 8 to 7V by 8, then what is going to happen? If it is lies between 6V by 8 to 7V by 8, then up to C6 all are activated. So C1, C2, C3, C4, C5, 6, C6, we are going to get high voltage here, but this one is 0. So out of these 6 is having more priority when compared to other. So for 6, we are going to get the corresponding binary output, which is 1, 1, 0. So you can see clearly from here. Suppose if VA is greater than 7V by 8, then what is going to happen? If VA is greater than 7V by 8, then all have been activated. All have been activated because their positive terminal voltage is greater than negative terminal voltage. So all are being activated. So all are I we are going to get. So if all are I means out of this, 7 is having more priority when compared to other. So corresponding to 7, you are going to get the binary output, which is 1, 1, 1. So this is the diagram that you are going to get. So this is the table that you are going to get. So therefore we can see that very important, the resolution or the step size, the minimum voltage that which can be measured with the help of this flash type ADC is V refresh by 2 to the power of n, which is the voltage drop across the each and individual resistor. So this is a point that you always have to keep in your mind. But this is not an accurate method. You can see clearly if V is greater than 7V by 7 VR by 8, if it is very high, still you are going to get the same result. So therefore you can see this is not an accurate method, but you are going to get the result very fast. But this is not an accurate method. You can see clearly, see if V is any value which is greater than 7 VR by 8, you are always going to get the same binary output. But this is not the true value because your V is somewhat greater than 7 VR by 8. We want the actual value, but we are getting a value no matter what is the V greater than 7 VR by 8. For all the things you are going to get the same output. But we can say this is the fastest method, but this is not the accurate method. We are not accurately measuring what is the analog voltage in terms of digital format. So we can say this is not accurate method, but this is a very fastest method. Within 1 tick clock only we are going to get the result. See, suppose if you take some voltage VA, suppose if you take some voltage VA and you have counted here. So out of these all things, out of all these things, one combination that it is always going to satisfy. So one combination we are going to satisfy and we are going to get the corresponding binary output we are going to get. So we can say no matter whatever the input, listen carefully, no matter whatever the input, always out of these, one combination is always going to get satisfied. So you are going to get the corresponding binary output you are going to get. So therefore, if you try to make it as a decimal equivalent, if you try to make it into a decimal equivalent of this binary output, you may think that is called as the analog voltage, that unknown analog voltage. So we can say no matter whatever the input voltage you apply, so no matter whatever the input voltage you apply, analog input voltage, unknown analog input voltage, out of all these combinations, one combination is always going to get satisfied and you are going to get the corresponding binary output you are going to get. This is what I am trying to tell you. So therefore, no matter whatever the analog voltage, you are going to apply unknown analog voltage. Always out of this one combination is going to get always satisfied. So you are going to get the corresponding binary output. You can say always only one time, which is 1 T clock. Within 1 T clock only you are going to get the result. So no matter what are the analog voltage. So that is the reason we can say the time conversion. The time conversion is independent of the input voltage. No matter what are the input voltage, it is taking same time to get the output. We can say binary output. So corresponding binary output. So that is the reason it is called as the independent of the. That is what is called as the independent of the input voltage. And time is always the maximum time conversion is equal to T clock. Within this T clock only you are going to get the result. No matter whether it can be true, whether it can be false, but you are going to get the result within this T clock only. But definitely there will be an error between the actual value and the value that you have got. So this is a point that you always have to keep in your mind. Now we are going to learn about the dual slope ADC. Dual slope ADC is the last, we can say last ADC in the ADC concept. I have already told you the remaining all ADCs. This is the last one. It is called as the dual slope ADC. So this is basically the last ADC in the concepts. So listen carefully regarding this dual slope ADC. So it is a very slowest and it is very accurate. So as a result it is very slowest, but you are going to get the result accurate. Same thing in life also. Sometimes you may be slow in achieving things, but definitely you are going to achieve the success. No matter it may be slow, but definitely you are going to achieve it because consistency is required. No matter how many failures you face, definitely you are going to achieve it. If you have that consistency, definitely you are going to achieve the success. So don't worry regarding all these things. So dual slope ADC means it is basically a slowest one, but it is a very accurate one. So S means easily to remember, which is a very slowest and it is a very accurate way to get the corresponding binary result of this input analog voltage. So you can see clearly this is a VA. VA is called as basically here VA means the unknown analog input voltage that I want to measure. So here there is a op amp like this. You can see clearly there is a resistor, there is a capacitor. So it is going to function like a, see you can see clearly it is going to function, how it is going to function? It is going to function like a integrator. So it is going to function like a integrated circuit. It is going to function like a integrator. Then there is an open loop op amp. You can see clearly whatever this output voltage, it is going to feed back to this open loop op amp. So this open loop op amp is going to give you the output voltage to AND gate. So what is the AND gate? For one time, for one input there is a clock signal and the other input is going from this open loop op amp. Then it is going to give to the up counter. So up counter is going to basically increase the values from 0, 1, 2, 3 like this. So we are going to use now 4 bit or 8 means 4 bits we are going to choose here. So now then out of this only MSB bit we are going to take it to this. We can say this is called as we are going to give to the this is called as the clock generator. It is a basically a negative edge triggering. It is basically a negative edge triggering. So it is going to act like a negative edge triggering. It is a negative edge triggering. So we are going to do like this. So whenever Q changes, whenever the Q3 changes from 1 to 0, then only this Q is, the output is going to get changed because it is in the toggling mode. So therefore whenever this Q3 changes from 1 to 0, then the negative edge triggering is going to get occur and then this Q is going to get changed. So therefore the switching is going to get changed. The switching is going to get changed. So this is we are going to do this switching. So basically we are going to give the switching like this. So basically initially we are going to connect this switch to the minus VR voltage. So initially we are going to give the switch to the negative voltage. After some time when this negative triggering is occurred, we are going to make the switch to this unknown voltage VA. By this we are going to figure out this corresponding binary output voltage to the corresponding analog input voltage. So initially we are going to connect the circuit to the negative reference voltage. This value we know. So now after some time whenever there is a negative triggering occurred, then we are going to switch to the VA voltage, the analog input voltage that we don't know. We have to connect the switch and then basically we are going to figure out this value. So listen carefully how we are going to get this one. See, this is basically we can say integrated circuit. This is basically an integrated circuit. Suppose whatever this VIN is basically a DC nature. Suppose if this is a DC nature, suppose this is a DC nature means constant signal, then for a constant signal, if you apply this, we can say this is a resistor, this is a capacitor, so this is the current I. So as here it is the current is equal to 0 and current here also it is 0, so this voltage is equal to this voltage. So if you apply the principle, I is equal to VI IN minus 0 by R is equal to I is equal to C dV by dt means 0 minus V naught by dt. So if you solve this one, we are going to get V naught is equal to minus 1 by RC integration of VIN into dt. As where is the constant, we can take it outside, and integration of dt is nothing but T. So we are going to get finally V naught is equal to minus VIN by RC into T. So this is basically an integrated circuit, So whenever the VIN is a constant signal, so we are going to get the output in this manner. So V naught is equal to minus VIN into RC into T. So listen, initially we are going to give the switch to minus VR. So in place of VIN, substitute here minus VR. So minus into minus is nothing but plus VR. So plus VR by RC into T we are going to get. So this is called as a plus VIN by RC into T we are going to get. So listen carefully. Initially, we are going to connect the switch to the VA, not VR. So minus VR. Actually, we are going to connect the switch initially to the VA, not minus VR. So as initially we are going to connect the switch to the VA. Then what is going to happen? I have already told you, whenever VIN is nothing but VA, so we substitute here minus VA by RC into T. So we are going to get negative voltage. So output voltage of this one is negative voltage. So we are going to get negative fashion like this. What is the slope? Slope is equal to minus VA by RC. So slope is equal to minus VA by RC. So initially the switch we are going to connect to the unknown voltage VA, and later we are going to connect to the reference voltage minus VR. So this is a small mistake I did. So please do correction here. So therefore here initially we are going to get V naught as negative voltage. You can see clearly as V naught is equal to negative and this positive voltage is 0. So 0 is greater than this negative value. So therefore this open loop R is going to give you plus V reference. So plus the V reference you are going to get here. So therefore this clock is going to get activated. So whatever this clock signal is going to pass through this one, because this is high. So clock signal is going to pass through this one. So therefore it is going to count the clocks. So therefore it is going to do the up counter. It is going to count this one. So therefore we are going to get the binary output. So therefore binary output is going to get increased like up counter. So this is the counter which is 0000, 0001, 0010. So it is going to count here. See, finally you are going to get 1111. So up to here it is going to count like this. So up to here it is going to count like this. Then you are going to get again initial point you are going to get 0000. So whenever the 000 comes, you can see clearly 120 means negative edge triggering. So this Q3 is changing from 1 to 0 means negative edge triggering has occurred. So therefore it is in the traveling mode. So Q is going to change from its output. Suppose let me assume initially it is a 0. So now it is going to become 1. So therefore the switches go to the now minus VR. Initially it is at the VA. Now it is going to move to the minus VR. So you can see up to this time, so output voltage is following the slope of minus VA by RC, But at this instant, a negative triggering is occurred. So therefore, now the input voltage is minus VR. So if you substitute in place of VA in minus VR, we are going to get plus VR by RC into T. So slope is positive. So we are going to get a positive slope of VR by RC, because in place of VA in, you have to substitute minus VR. So therefore, minus into minus is plus. So plus VR by RC we are going to get. So plus VR by RC is the slope that we are going to get. So this is the slope that we are going to get here. So you can see clearly this is the slope that we are going to get. So now what I have to do? So now again the counter is going to get count, because always V naught is equal to negative. Up to here V naught is equal to negative. So V0 is equal to negative means this is positive. So whatever this clock is going to go through this one, so counter is going to count here. But listen carefully, the voltage is going to get decreased. The voltage is going to get decreased and it is going to become 0. It is going to become 0 and it tries to become positive. When it tries to become positive, listen carefully, when it tries to become positive, so whenever V0 is positive means this is greater than this value, so it is going to become 0. If this is 0, then this is also 0. So counter is going to stop the count. So therefore, whenever the voltage tries to become positive, the counter is going to stop its counting. So let me assume this is the ABCD. So this is the counter at the edge of voltage become positive. Whenever the output voltage tries to become positive, at the edge it is going to become off, and this is the counter is going to indicate, which is ABCD. So let me assume the counter is indicating a count like this, which is ABCD. So this is the time T1 and this is the overall time is T2. So this is the time T1 and this overall time is T2. So this is the time for 0 to T1 is the time for which the switch is at the VA, and T1 to T2 the switch is at the minus VR. So the number of cycles is nothing but, the total number of cycles is nothing but to the power of n cycles. Therefore this total cycle is nothing but to the power of n. But the decimal value is to the power of n minus 1. But the total number of cycles are to the power of n. So this total cycles, if you count from here to here, then you are going to get to the power of n cycles. For 4-bit means 16. So 16 counts you are going, means 16 clock cycles you are going to get here. So to the power of n cycles you are going to get here. From here to n, let me assume these are the n cycles, some n cycles. So within these n cycles, it is going to get stopped. So from here to here, let me assume these are the n cycles. So what is the maximum value? This maximum value is nothing but at T1. At T1, what is the value? This substitute in this expression. So initially, the switch is at the VA. So therefore, minus VA by RC into capital T1. So minus VA into T1 by capital RC. So this is the maximum value that you are going to get. So this is the voltage that you are going to get, because the ramp signal means you are going to get negative slope here, but here positive slope, so voltage should decrease. So it tries to become positive. If slope is negative means this is in the downward direction, slope is positive means it is rising. So at the edge of becoming voltage positive, the count is going to get stopped, and this is the voltage that you are going to get. This is basically the count is going to indicate like this A, B, C, D. So now I have already told you, let me assume whenever the switch is equal to 0 means Q is equal to 0, and I am going to assume initially Q is equal to 0. So whenever Q is equal to 0 means switch is equal to 0 means the input voltage is equal to VA. I have already told you, initially the switch is at the 0 means it is at the VA. So whenever the triggering occurred, then Q is equal to become 1. So Q is equal to 1 means switch is equal to 1 means the input voltage is equal to minus VR. So initially the switch is at the VA and later the switch is at the minus VR. And the number of clock cycles here is to the power of n clock cycles, and here it is n clock cycles. So initially counter and the T flip-flop was reset to 0. I have already told you, initially counter and the T flip-flop was reset to 0 means this value is 0, 0, 0, 0, and this is also 0. So initially we are going to make the counter as well as the T flip-flop was at 0 means this P is equal to 0, this count is also 0. So whenever P is equal to 0 means X is equal to 0 means the input is equal to VA. At T is equal to T1, output of T flip-flop was changing from 0 to 1. I have already told you, and T is equal to T1, Q3 is changing from 1 to 0 means negative edge triggering. So negative edge triggering happens, so therefore Q0 is going to change from 0 to 1. So at T is equal to T1, output of T flip-flop was changing from 0 to 1. So up to T is equal to T2, counter continuously increments, after that it stops. I have already told you, after T2, just at the edge of T2, voltage tries to become positive, so counter is going to become stop its counting. So this is the which we can say just at the edge of stopping, this is the value which is shown by the up counter. So up to T is equal to T2, counter continuously increments, after that it stops. The number of cycles up to T1 is nothing but, the number of cycles up to T1 is nothing but, which is to the power of n. So the number of cycles up to T1 is nothing but to the power of n, and the number of cycles from T1 to T2 is n. I am going to assume these are the n number of cycles. So n number of cycles from T1 to T2, I am going to assume these are the n number of cycles. So n number of cycles. Then T1 is equal to, what is T1? T1 is equal to the power of n into T clock, and T2 minus T1 is nothing but n into T clock. So T1 is equal to the power of n into T clock, and T2 minus T1 is equal to n into T clock, where small n is called as the number of binary bits in counter. Small n is the number of binary bits in counter, and capital N is called as the decimal value of counter read at the instant T2. So you can see clearly this is the decimal value ABCD. So if you go for the decimal value of this ABCD, it is nothing but it is equal to n. So therefore we can say clearly the decimal value of this ABCD is nothing but this is n. So capital N is nothing but the decimal value of this ABCD. The decimal value of this ABCD at the instant of T2. So n is called as the decimal value of the counter read at the instant T2. See, and I already told you it is always slowest and it is most accurate. This dual slope is very slowest and it is very accurate. Then what is the maximum number of clock pulses? Maximum number of clock pulses means I already told you initially it is to the power of n, and here also we can get to the power of n, because if it maximum is I already told you the n can be maximum, it can become up to the power of n only. The minimum value is 0 and the maximum value is to the power of n. So to the power of n plus to the power of n is equal to the power of n plus 1. So this is the maximum number of clock pulses that are required. So therefore number of clock pulses used are nothing but practically the number of clock pulses used are to the power of n plus capital N. As VA increases, then what is going to happen? As VA increases, then T1 is always fixed, because T1 is fixed means it is going to depend only on the clock pulse, whereas the T2 is going to get increased because the peak value increases, so therefore T2 also increases. See, basically what I am trying to tell you, if VA increases, what is going to happen? If VA increases, then this slope is going to get increased. So this slope is going to get increased. So this graph is going to become like this. But this time is constant. Though, so whenever the VA increases, the slope is increases. So therefore, but this time is a constant. So graph is going to become like this, and this is going to become like this. So you can see clearly. From this picture. See, whenever the VA increases, the slope increases, right? The slope increases. So therefore, the slope increases. So therefore, but T1 is always fixed. T1 is only depending upon to the power of n cycles. So it is always fixed. So therefore, now this line slope is always equal to this line slope. So therefore, these two should be parallel. So therefore, its overall time will increase. So this n cycles will increase. So therefore, we can say for finally, whenever the VA increases, T1 is fixed, the peak value increases. So this first line slope increases. But this line slope is always equal to this line slope, so both are parallel. So therefore, this total time will increase. So the number of n cycles, these cycles are going to get increased. As VA increases, the T1 is fixed and T2 increases. I already told you. So therefore, as this T2 is going to get increased, I already told you. So therefore, now what is the expression of V naught of T? So V naught of T is equal to, from T1 to T2 I want to figure out, because I already told you the expression of V naught of T for T less than T1. For T less than or equal to T1, I already told you, which is minus VIN by RC into T. As for for T less than T1, what is the input voltage is equal to VA, so minus VA by RC into T. But for T1 less than or equal to T less than or equal to T2, now what is the output voltage? V of T is equal to minus VA by RC into T1 plus VR by RC into T capital small t minus T1. Because it's a peak value, which is minus VR by RC into capital T1 plus which is VR by RC into T minus T1. So this is the thing that we are going to get. Now at T2, the output voltage is going to become 0. So at T2, we are going to get the output voltage is equal to 0. So if you substitute here, in place of T, substitute capital T2 and we can keep this one 0. So we are going to get this expression, which is Vj is equal to VR into n by to the power of n. Then what is n? N is nothing but T2 minus T1, because n is nothing but simply I have already told you here VR into n by to the power of n we are going to get, which is equal to VR into T2 minus T1 by T1. So T2 minus T1 is nothing but n into T clock, but T1 is equal to the power of n T clock. So T clock cancels. Finally, we are going to get VR into capital N by to the power of n. Or finally, VR into T2 minus T1 by T1. That T2 minus T1 is called as the deintegration time and T1 is called as the first integration time. So this is a very important one. T1 is called as the first integration time and T2 minus T1 is called as the de-integration time. So we can easily find this value of n. We can easily find this value to the power of n, and we also know the value of Vr. So with this data, we can find what is the value of the Va. So with the help of this dual slope, we are going to find this value of the unknown analog input voltage. Va is equal to V reference voltage into T2 minus T1 by T1. So T2 minus T1 is nothing but capital M into T clock by, and this T1 is equal to the power of m into T clock. So therefore, simply we can say if T clock cancels, we are going to get Vr into capital M by to the power of n. So this is a very important formula that you always have to remember. T2 minus T1 is called as the de-integration time and T1 is called as the first integration time. So this is called as the dual slope ADC. So let me repeat this one. So initially I am going to give the switch to the VA, and after some time automatically whenever is a negative triggering happen, the switch is going to become 1. So therefore it is going to move to minus Vr. So therefore from this, whenever the negative triggering happen, so the switch is going to move to minus Vr. Then I already told you always this time is fixed. 0 to T1 is always fixed. Only from T1 to T2 it is a variable because the slope is always constant, but as the Va increases, this peak value increases. So therefore these two lines are parallel to, so this T2 is going to get increased, but T1 is always fixed. So these are the important points that you always have to keep in your mind. So T1 is also always equal to the power of n T clock, and this T2 minus T1 is equal to capital M into T clock, where capital M is the decimal equivalent of this ABCD. Or we can say at the instant of T2, what is the value of the up counter reading, you have to go for decimal equivalent of that. So let me do a small revision of this concept again. Dual slope ADC. See, the name itself, AC indicates it is a very slowest and it is a very accurate method. So this is the circuit which is going to be here. So this is a unknown voltage that we want to measure, and this is the reference voltage of negative side. This is the switch, this is the resistor. So initially we are going to connect the switch to the VA, and later we are going to connect to VR, minus VR. So this is basically a integrated circuit. So what is the output voltage? Output voltage is equal to minus VIN by RC into T. So here there is a op amp. So this V0 we are going to go to the negative terminal. So whenever this voltage is greater than this voltage, we are going to get V reference. Whereas whenever this voltage is greater than this voltage, we are going to get 0 here. So therefore, if this is positive means high voltage means whatever this clock is going to pass through this output, so count is going to get increase its counting. Whenever this becomes 0, so overall value will become, so count is going to stop its counting. See, listen carefully. There, this Q3 we are going to give the negative triggering. So this is basically acting like a T flip-flop means T is equal to 1 means it is acting in the toggling state. So initially we are going to make Q is equal to 0, and also this count is also at the 0 condition. After some time, whenever this Q3 is changing from 1 to 0, a negative trigger is happened, so therefore Q is going to change from 0 to 1. So initially Q is at 0 means S is equal to 0, it is at the VA. After some time, whenever S is equal to 1 became, it is going to connect to minus VR. So this is the circuit that we are going to see here. So I have already told the operation, this is the output voltage. See, initially we are going to connect to the VA. So the slope is nothing but minus VA by RC we are going to get, because V0 is equal to minus VIN by RC into T. As VIN is equal to, here basically we are going to get initially VA. So slope is equal to minus VA by RC into T expression 2. So T minus slope is equal to minus VA by RC. So it is a ramp signal of negative slope. So it is going to increase in this fashion. As it increases, you can see clearly the count is also counting, it's incrementing its count. So as the count is incrementing, and finally it is going to reach a value of 1111. See, whenever it becomes 1 to 0, again it is a loop fashion, 0 0 0 0. So there is a negative triggering occurred. So now switch is going to change from 0 to 1 means it is going to move to now minus VR. So whenever the minus VR as the input, then what is the output expression, which is VR by RC into T. So it's a ramp signal of positive slope. So slope is equal to VR by RC. So like this it is going to increase. Now voltage is going to get increased. So at the edge of this one, whenever the voltage tries to become positive, I already told you whenever V0 tries to become positive, the output of the open loop op amp is going to become negative, or we can say 0. So therefore, the output of the AND gate is 0. So therefore, the counter is going to stop its counting. So this is the last at the edge of T2. This is the countering. It is going to stay for all the time. So this is the ABCD. I am going to assume it's the counting at the start, at the ending, or at the ending end. So this slope is minus VR by RC, and this slope is VR by RC. So this total number of cycles are nothing but 2 to the power of n cycles, because from 0 0 0 0 from 1 1 1 1 generally for n bit we are going to get 2 to the power of n cycles. But for bit we are going to get 16 cycles, so 2 to the power of n cycles. Similarly, for this one I am going to assume these are the n cycles. N is nothing but it is a decimal value of this ABCD. So therefore, the total time is nothing but this time from T1 is equal to the power of n into T clock, and this time T2 minus T1 is equal to n into T clock, where n is the decimal equivalent of this ABCD. So listen carefully, whenever the VA increases, what is going to happen? Whenever the VA increases, the slope increases, so graph is going to become like this, and after that, this line has the same straight line, same slope of this line, so therefore T2 will increase, but T1 is fixed, T2 increases, this peak value increases. So these are the things that you need to understand. So what is the conversion time is also increases. So it need this much amount of time. It need this much amount of time. So therefore, this total time is going to get increased. So whenever the input voltage increases, you can see the conversion time is also increases. The conversion time is also increases. So therefore, we can say whatever this through this dual slope, we can say that ADC, as the input voltage increases, the conversion time is also increases, because we need, I already told you what is the formula. VA is equal to VR into T2 minus T1 by basically we can say that which is T1. So as T2 minus T1 increases, because as the VA increases, so therefore simply we can say the VA increases means T2 minus T1 increases means conversion time is also increases. So that is the reason whenever the input voltage increases, the conversion time increases. So therefore this dual slope ADC is depending upon both the number of bits and also on the input voltage. This is the point that you always have to keep in your mind. Then what is the maximum conversion time? So this n can be maximum, it is to the power of n. So to the power of n plus to the power of n is equal to the power of n, or simply we can say to the power of n plus 1. So total the maximum conversion cycles are to the power of n plus 1 cycles. So all I told is the integrated circuit. So this is the VIN. So V0 is equal to minus VIN by RC into T. And all I told you, whenever the switch is equal to 0, it is at the input voltage is equal to VA. The switch is connecting the VA. Whenever the switch is equal to 1, what is the input voltage? Which is the switch is connecting the minus VR. So VIN is equal to minus VR. So initially I assume the counter and the T flip-flop was reset to 0. At T is equal to T1, output of T flip-flop was changing from 0 to 1. So therefore a negative triggering is occurred. So therefore the switch is going to move from VA to minus VR. Up to T is equal to T2, counter continuously increments, after that it stops, and what I told after that voltage tries to become positive. So therefore whenever V0 tries to become positive, this value will become 0. So this value will become 0. So therefore this counting is going to get stopped. So the number of cycles of T1 is equal to the power of n cycles, and the number of cycles from T1 to T2 is n cycles. N is the decimal equivalent of the ABCD. This is the counting at the ending end. So what is T1 to the power of n T clock, and T2 minus T1 is equal to n into T clock. And the small n is called the number of minor bits in the counter, and capital N is called as the decimal value of the counter, which is read at the instant T2. It is the slowest and very accurate. I already told you the maximum number of clock pulses is nothing but to the power of n. Here n is the maximum value of n is equal to the power of n. So to the power of n plus to the power of n is equal to the power of n plus 1. So the number of clock pulses used are called as the total is 2 to the power of n plus 1 n. So n maximum value is to the power of n. So this value we are going to get to the power of n plus to the power of n is equal to the power of 2 into 2 to the power of n is equal to the power of n plus 1. That is the maximum number of clock pulses required in order to detect the output. In order to detect the output, it is a maximum number of clock pulses. See, as V increases, I already told you the peak value increases, so T1 is fixed and it is going to get increased. So what is the output voltage expression whenever T less than T1? Whenever T less than T1, the output expression I already told you, which is minus VA by RC into T. Whereas for T1, for T lies between T1 to T2, the output voltage expression is minus VA by RC into T1 plus VR by RC into T minus T1. So I already told you at T2, the output voltage is equal to 0. So if you substitute here and you simplify this one, we are going to get VA is equal to VR into T2 minus T1 by T1. Where T2 minus T1 is equal to N into T clock and T1 is equal to the power of N into T clock. So T clock cancels. We are going to get VR into N by to the power of N. So T2 minus T1 is called as the de-integration time and T1 is called as the first integration time. So these are the things that you always have to keep in your mind. So now we are going to learn some important simple concept. You can see clearly here. So there is a 2-bit counter. So this is a 2-bit counter. You can see clearly here. This is a 2-bit counter. So we are going to give input as a clock. So input as a clock. So this is the Q0 and this is the Q1. So Q0 is the LSB and Q1 is the MSB. So we are going to give this input to this decoder. So then we are going to get the output. I already told you for a decoder, it is basically decoder is nothing but it is going to convert the binary format to any other number system. So now I have already told you for decoder, it is basically it is the inverse of, or you can say it is going to function like a mux. So basically it is going to function like a mux or receive. If you go for the demux, I have already told you for demux. Demux is nothing but the number of inputs are 1 but the number of outputs are many. So we can say here it is for demux which is 1 cross to the power of n. But if you interchange the number of select lines and the input lines of demux, then we are going to get the decoder. So this is the decoder. So for decoder, the general expression is n cross to the power of n. So for n inputs, we are going to get to the power of n outputs. So this is basically a simple circuit. You can see clearly from this figure. So it is a 2-bit counter and also a 2x4, 2 cross 4 decoder, because 2 inputs means 2 square is nothing but n cross to the power of n. If n is equal to 2, so n cross to the power of n is equal to 2 in 2 cross 4. So this is basically a decoder. So it is going to convert the, so 2 cross 4 basically decoder is going to convert the binary format to any other number system. So now I want to basically analyze this circuit. So it's a combination of decoder and also a counter and a decoder. So now I want to see what is the counter outputs. So these are the counter outputs. So it's a 2-bit counter. So this is MSB and this is LSB. So counter is going to do the counting operation. Let me assume this is the up operation. Count is the, or you can say upward operation. So up counter. So 0 0 0 1 1 0 1 1. Then what are A, B? AB are the inputs. So Q1 is equal to A and Q0 is equal to B. So what are the decoder inputs? So Q1 is equal to A and Q0 is equal to B. So therefore same thing we are going to get 0 0 0 1 1 0 1 1. Then what are the outputs? Let me assume the outputs. The decoder outputs are the D0, D1, D2 and D3. So D3 is the MSB and D0 is the LSB. So D3, D2, D1, D0. So D0 is the LSB and D3 is the MSB. So whenever you are giving 0 0, then which is going to get activated? This 0 is going to get activated. Remaining things are not activated. So therefore this D0 is activated but not the remaining things. So if you give 0 1, this 1 is going to get activated but not the remaining thing. So D1 is going to get activated but not the remaining thing. If you give 1 0, this 2 is going to get activated but not the remaining thing. So therefore this is going to get activated but not the remaining thing. So if you give 1 1, this 3 is going to get activated but not the remaining thing. So D3 is going to get activated but not the remaining things. So you can see clearly. The one is shifting. The one is shifting in this direction. So we can say this one came here, this 0 came here, this 0 came here. In the next position, this one came here, this 0 came here. In the next position, this 0 came here, this 0 came here, this one came here. So listen carefully. Initially, 1 came to here, 0 came to here, 0 came to here. So now, this 0 came to here, this one came to here, this 0 came to here, and this 0 came to here. Similarly, you can see clearly, again, this 0 came to here, this 0 came to here, this one came to here. Or in another fashion also you can do like this. Very simple. This 0 came to here, this 0 came to here. So you can see this is the thing that you always have to keep in your mind. So therefore, this one came to here, this 0 came to here, this 0 came to here, and this 0 went to here. Similarly, this 0 came to here, this one came to here, this 0 came to here, and this 0 came to here. Again this 0 came to here, this 0 came to here, this one came to here, and this 0 came to here. So this is basically doing like a ring counter operation. So this concept I have already told you, one is shifting. So therefore we can say it is said to be a ring counter. The overall circuit is going to act like a 4-bit ring counter. So whatever this overall circuit, the combination of 2-bit up counter and the 2 cross 4 decoder, this whole circuit is going to act like a 4-bit ring counter, because the input one it is shifting one after the another. You can see clearly from this table itself, one is shifting slowly one after the another. So we can say it is going to, the overall circuit is going to act like a 4-bit ring counter. So you can see clearly the overall circuit is going to act like a 4-bit ring counter, because we can say clearly the output is changing from, so the output one is changing through small amount of shift at each and everything. So the overall circuit is going to act like a 4-bit ring counter. So now let me tell you one more simple concept here. Suppose if a counter having 10 flip-flops, suppose if a counter is having 10 flip-flops is initially at all zeros. Suppose if a counter is there, it is having 10 flip-flops is initially at all zeros, means all are having the zeros. So what count will it hold after 2060 clock pulses? So basically in this question they are given that here there is a counter which is having the 10 flip-flops. Initially all are having the 0. So what count will it hold after 2060 clock pulses? We need to figure out. So after 2060 clock pulses, what is the count is there in this counter we need to figure out. So based on this, now we are going to solve this one. Listen carefully. Given counter is having 10 flip-flops, therefore it will count from 0 with a base 10 to 1023 with a base 10, because I have already told you, suppose if there are 10 flip-flops, 10 flip-flop means each flip-flop is going to give you 1 bit. So therefore 2 to the power of n minus 1. So then the count, the maximum count is equal to, in the decimal format, which is 2 to the power of n minus 1, which is 2 to the power of 10 minus 1, which is 1024 minus 1 is equal to 1023. So in the decimal format, it is going to represent, the range of representation in the decimal format is from 0 with a base 10 to 1023 with a base 10. So this is what it is going to tell you. So it is having total number of 1024 states. So how many states it has? It has total 1024 states, because I already told you 0 is a 1 state, 1 is a 1 state, 2 is a 1 state, up to 1023 is also a state. So if you count all these states, then you are going to get 1024 states we are going to get. So total states are 1024, but the maximum decimal number, the range of decimal number is from 0 to 1023. So now in this question they are telling that after 2060 clock pulses, what is the count we need to figure out. So first thing is we have to subtract 2060 from this state, which is 1024 total states. Then we are going to get 1036. Again you subtract again 1024, you are going to get 12. So you have to get a number. See, always try to get a number which is in the states only. So try to get a number which is in between the states. So you can see clearly 12 lying between the states, because 12 is going to lie between 0 to 1024, whereas 1034 is above the 1024. So I want a number which is lying in between the 0 to 1024 states. So I want a number which is lying in between the 0 to 1024 states. That is the reason I have subtracted 1024 two times. So therefore 2060 minus 1024 is 1036. Again 1036 minus 1024 is equal to 12. So 12 is the number is lying between the 0 to 1024 states. The value of counter after 2060 pulses is same as that after 12 clock pulses. So finally in this question we are going to say that what is the value of the counter after the 2060 clock pulses is the same as the counter output after the 12 clock pulses. It's a very important concept. So whatever the counter is showing after the 2060 clock pulses is the same as the counter output after the 12 clock pulses. So what is the value of 12? So 12 is nothing but 12 clock number in terms of decimal format is 10. So what is in terms of binary, which is 11002. So we can say 12 in terms of, this is the in terms of decimal. So now I want to find in terms of the binary, which is 1100 in terms of binary format. So after 2060 pulses, the counter will be, therefore, so after 2060 clock pulses, the count will be 11002 in the binary format, or you can also write like this, which is 000000110002, because it is having a 10 counters with 10 flip-flops, so total number of digits must be 10. So therefore 1 2 3 4 5 6 7 8 9 10. So total we are going to have 10 places. So therefore this is the 12 we are going to get in this binary format. So this is the point that you always have to keep in your mind. So whatever the counter we are going to assume, basically it is a up counter. So whatever the counter we are going to assume, it is basically up counter. So this is a very important point that you always have to keep in your mind. So we can say that, see, whatever we have done, 10 is very simple. So whatever, say given counter is having 10 flip-flops, so therefore it will count from 0 with a base 10 to 1023 with a base 10. So it is having total number of 1024 states. So we are subtracting 2060 from 1024, we are going to get 1036. Again we have subtracted 1036 minus 1024, we are going to get 12. So what is the value of the counter after 2060 clock pulses is same as that of after the 12 clock pulses. So 12 clock pulses means, here you can see clearly after 12 clock pulses. It's a very important point. So after 1 clock pulses you are going to get 0001. After 2 clock pulses you are going to get 0010. So like that we have to do this one until you get the 12. The decimal format of 10 is nothing but 1100. It's up counter. So therefore after 2060 clock pulses, the count will be in this format with the 10 places. So this is basically a 12 number in the format of decimal, number it is 12, and this is a representation in the binary format. So you can see clearly I have represented something very important. So initially I am going to assume, I am going to take only 4 counts. I am going to take only the first 4 only 4 flip-flops I am going to consider like this for easy purpose. So therefore this is the clock pulses and this is the output count. Initially I am going to assume all are having the 0 output, all are 0. Suppose after the first clock pulse the count is 0001, because it is the up counter we are going to assume. So after second clock pulse it is going to give you 0010. Similarly after third clock pulse you are going to get 0011. So up to, if you go for the after the 12th clock pulse you are going to get 1100. So this is the binary format of this 12 decimal number. So therefore we can say that after 12 clock pulses you are going to get 1100 in terms of 4 digits. But if you want in terms of 10, you have to extra the remaining digits, you have to keep here zeros. All the zeros you have to keep here. So this is a concept that you always have to keep in your mind. So after first clock pulse you are going to get 0001. After second clock pulse you are going to get 0010. After third clock pulse you are going to get 0011. So after that, after 12th clock pulse you are going to get, if you extend in the same process, so after 12th clock pulse you are going to get 1100. In terms of 4 digits only I have written, but if you want in terms of all the 10 digits means you have to keep here the remaining digits as zeros, because it is a up counter. So we are going to assume it is a up counter. So this is the thing that you always have to keep in your mind. We are going to study one more important simple concept. So listen this circuit here. So there is a op amp here. So you can see clearly for this op amp there is a feedback from output to the inverting terminal. So this is called the negative feedback. And also the input is applied to the inverting terminal. So it is basically an inverting op amp. So now you can see clearly this resistance is R2 and this is R3 and this is R4 and this is R5 and this is R1. So now we have to find what is the expression of output voltage V0 in terms of Vi. As you can see clearly, the circuit, as we are going to apply, as the input currents are 0 here and input currents are 0 here. So with the help of absolute short circuit, whatever this voltage should be equal to this voltage. So therefore, these both voltages are same. So now if you see clearly, this is the input voltage and this is the 0 voltage. So if you want to find the current of this one, so current in R2 is equal to Vi by R2 and current in the R3 is equal to, which is Vi by R3. But the currents in R4 and R5, as this potential is 0 and this potential is also 0, so the currents in both of them is equal to 0. So therefore only these two currents are going to enter here, and whatever is entering current should flow through this R1 because here it is always equal to 0 current. So therefore this current is going to pass through this one. So 0 minus V0 is equal to R1 into 0 minus V0 is equal to R1 into IF. IF is nothing but it is a summation of these two currents. So therefore if you do a simplification, finally we are going to get V0 by Vi is equal to minus of R1 by R2 plus R1 by R3. So there is nothing like R4 and R5 terms. So if you do like that, we are going to get the V0 by Vi is equal to minus of R1 by R2 plus R1 by R3, because IF is equal to summation of Vi by R2 plus Vi by R3. So if you substitute in place of IF is equal to V1 by R2 plus Vi by R3, then if you simplify this one, we are going to get V0 is equal to V0 by Vi is equal to minus of R1 by R2 plus R1 by R3. So this is the very important point that you always have to keep in your mind. So now we are going to study one more important simple concept. So listen carefully. A clock of frequency 1 megahertz. So a clock of frequency 1 megahertz with 40% duty cycle is applied to the following circuit. So there is a clock of frequency 1 megahertz with a duty percentage of 40% duty cycle is applied to the following circuit. In order to eliminate the race around condition, the propagation delay of the flip-flop must be. So in order to eliminate the race around condition, the propagation delay of the flip-flop must be. So in this question they are asking, so whenever you are going to keep J is equal to 1 and K is equal to 1, there is a race around condition. Race around condition means the amount of the output variation is very speed from 1 to 0, 0 to 1 like a super fast rather than the express. So it is going to move very fast. So this is called as the race around condition. So in this we are going to give a clock frequency of 1 megahertz with a duty cycle of 40%. Then in order to eliminate the race around condition, what is the propagation delay of the flip-flop? We must always apply. So see, I already told you, if the the propagation delay of the flip-flop is always lesser than the time, means we can say the on pulse width of the clock, and also it is less than the over time clock period. I already told this important expression, which is I have already told this important expression. So we know the propagation delay of the flip-flop is lesser than that we can say T1 of the clock is lesser than the T clock. Then we are going to compulsory get the race around condition. I have already told you this important point in the concepts only. So therefore we know that the propagation delay of the flip-flop is lesser than on time period of the clock is lesser than the clock time period. Then definitely we are going to get the race around condition. So now we'll discuss something more about this one. So then what is the TPD should be in order to avoid the race around condition means this TPD should be greater than T1. Then only this race around condition we are going to eliminate. So we have to find what is the value of TPD, the range of TPD in order to avoid the raise around condition. So here the clock frequency is equal to 1 megahertz. So what is the time period of the clock? And 1 told T clock is equal to 1 by F clock, which is if you substitute here we are going to get 1 microsecond. So what is the percentage duty cycle? It is on time period by total time period, which is T1 by total time period of the clock, which is T1 plus Tf into 100 is equal to, so we are going to get T1 by T clock, T1 plus Tf is equal to T clock into 100. So this is 40%, 40 is equal to T1 by 1. T clock is nothing but 1 microsecond. So therefore, if you substitute here, we are going to get 1 microsecond into 100. So if you solve this one, the T1 is equal to 0.4 microseconds. Say the propagation delay of the flip-flop, say TPDFF. The propagation delay of the flip-flop is, we are going to assume TPDFF should be such that in order to eliminate the race around condition, see I have already told you here, this propagation delay should lie between the T1 to T clock. Then only we are going to eliminate that. Then only we are going to eliminate the race around condition. So therefore, here the T1 is nothing but 0.4 microseconds and T clock is nothing but 1 microseconds. So if TPDFF, the propagation delay of the flip-flop is lying between the T1 to T clock, then we are going to eliminate the race around condition. So, but if the propagation delay of the flip-flop is lesser than T1 is less than T clock, then definitely you are going to get the race around condition. But if you interchange these two things, then we are going to eliminate the race around condition. So therefore, if T1 is less than TPD of the propagation delay of the flip-flop is less than T clock, then definitely you are going to eliminate the race around condition. But at this condition, we are going to definitely get the race around. But for this condition, we are not going to get the race around condition. So these 2 points that you always have to keep in your mind. Now we are going to start the one more important simple concept. So you can see clearly here, the modulus of the following asynchronous up counter is, assume that initially all flip-flops were clear. So here basically they have given a circuit. So they are asking what is the modulus of the following asynchronous up counter we need to figure out. And we have to assume that all the initial, you can say we have to assume that initially all the flip-flops were clear, means all are having the 0 outputs at the initial condition. So based on this we have to find what is the modulus of the following asynchronous up counter we need to figure out. The modulus of the following asynchronous up counter we need to figure out. So we have to assume that initially all the flip-flops were at the initial 0 condition, or they were clear. So you can see clearly this is the asynchronous up. Asynchronous means you can see clearly, see for one output of one flip-flop is triggering to the other flip-flop, then it is said to be asynchronous up counter. Otherwise, if all the flip-flops are excited by the same clock and all are being excited at the same instant, then it is called as the synchronous counter. Otherwise, it is an asynchronous counter. Asynchronous means the output of one flip-flop is given as a clock to the other flip-flop, then it is said to be asynchronous. Otherwise, if you are giving the same clock for all the flip-flops, so we are triggering each one at the same time, then it is said to be a synchronous counter. So therefore, we have to find what is the modulus of the following asynchronous up counter we need to figure out, and we have to assume that initially all the flip-flops were clear. So this is the circuit they have given in this question. So based on this we need to figure out. So this is a 4-bit. You can say 4 flip-flops means 4-bit. It is a 4-bit up counter. So this is the output. You can say this is the taking the outputs of Q3, Q2. So this is Q3 into Q2. This is basically Q2 into Q0 bar. So this is Q2 bar into Q0. So we are going to get here Q2 bar into Q0. basically if you see clearly, the output of this AND gate is nothing but Q3 into Q2, whereas the output of this AND gate is very simple, which is Q3 bar into Q2 into Q0. So Q3 bar into Q2 into Q0 is the output of this AND gate. So now we have to do the NOR operation, is addition, and take the complement of this. Then we are going to give this is clear input. So this, for this clear input we are going to give. Suppose if this is 0 means all these are going to get activated and everything output is going to become 0 default. If it is 1 means they are not activated, so it is going to be the counting up operation. So if the output of the NOR gate is logic 0, then all the flip-flops are cleared, because whenever the output of this NOR gate is 0, then all these clear operations are going to get activated and the output of all these flip-flops are going to become 0 irrespective of their previous state. So this is the point that you always have to keep in your mind. So if the output of the NOR gate is logic 0, then all the flip-flops are cleared irrespective of their previous position or previous output. So what is this F? F is nothing but, I already told you, this is nothing but Q3 into Q2, and this is Q3 bar into Q2 into Q0. So you have to take the whole bar. So F is equal to Q3 into Q2 plus Q3 bar into Q2 into Q0 whole bar. So now I want to become F to be low. So when F is low, at what conditions F is low, we need to figure out. So you can see clearly, whenever Q3 into Q2 is equal to 1, no matter whatever the other. So if Q3 into Q2 is equal to 1 means no matter whatever the other, definitely what is going to happen, no matter whatever the other, definitely you are going to get the output as 0. So 0. Or suppose if this is 1, if this term is 1, irrespective of this term, then also you are going to get the output as 0. So therefore, whenever Q3 into Q2 is equal to 1 or Q3 bar into Q2 into Q0 is equal to 1, if any of this 1 is 1, if any of these two terms, if it is 1, definitely output is always equal to 0. So Q3 into Q2 is equal to 1 only when both are 1. Yes. So Q3 into Q2 should be 1 only when Q3 is equal to 1 and Q2 is equal to 1. Otherwise, you are going to get 0. So therefore, Q3 should be always equal to 1 and Q2 should be always equal to 1. Then only we can say in an AND gate, 1 is the case only when both are 1. Because 0 into 0 is 0, 0 into 1 is equal to 0, 1 into 0 is equal to 0 and 1 into 1 is equal to 1. So both should be 1. Then only you are going to get the output as 1. So therefore, Q3 is equal to 1 and Q2 is equal to 1. So now for this case, if you analyze this one, what is going to happen here? If this is called as a min term, so min term is Q3 is equal to 0, Q2 is equal to 1 and Q0 is equal to 1. So Q3 is equal to 0, Q2 is equal to 1 and Q0 is equal to 1. So from both these things, what you have analyzed, if you analyze these two terms, definitely you have analyzed that Q2 is equal to 1 here, Q2 is equal to 1 here. So compulsory Q2 should be always equal to 1 and also Q0. So you can say Q0 is always equal to 1 here and Q2 is always equal to 1 here. Whereas Q3, here it is 1, here it is 0. So therefore it is, see whether Q3 can be 0 or Q3 can be 1. It can be anything. But Q2 should be always equal to 1 and Q0 should be always equal to 1. Q3 can be anything and also Q1 can be also anything because they are not given regarding this Q1. So Q1 can be anything, but Q2 should be always equal to 1 and Q0 should be always equal to 1 and the remaining things, the remaining terms can be anything. So therefore you can see Q3, Q2, Q1, Q0. So from these two things we have analyzed that Q2 should be always equal to 1 and Q0 should be always equal to 1. Whereas Q3 and Q1 can be any value, they can be 0 or they can be value 1. So now as in the question they have already mentioned, it is a up counter. So up counter means 4-bit up counter means it is reading from 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0. That here next count is 0, 1, 0, 1. So you can see clearly this is the, see Q2 is equal to 1 and Q0 is equal to 1. Only at this condition, only at this state, both are 1. You can see clearly this Q2 is equal to 1 and Q0 is equal to 1 only at this condition. So from here starting to here, so this is the F is going to now become 0 and it is going to trigger this all these clear inputs. So output is going to become default to 0. So therefore again we are going to go to this one. So how many stable states? 1, 2, 3, 4, 5. This is called a transient state. This is called as a transient state. So only 5 stable states are there. So it is called as the modulus 5 counter because it has only 5 stable states. So it is called as the modulus 5 counter. So it has only 5 stable states. So it is called as the modulus 5 counter. So this is an important point that you always have to keep in your mind. So transistor state you should not consider, only you have to consider the stable states. Only stable states you have to consider. So it is having only 5 stable states. So this is called as a mod 5 counter. And one more important point that you always have to keep in your mind. So add is up counter. So we have to increase the range for each one. So we have to add 1 to the LSB each and every time. So it is up counter. So at this condition you can see 1 is there, Q2 is equal to 1 and Q1 is equal to 1. Both these conditions satisfied. This can be anything. So at this lies or we can say this condition is satisfied. So it is going to become default 0. Here input is activated. So it is going to become 0. So only 5 states are there, stable states are there. So it is called as the modulus 5 counter. So now we are going to start with one more important concept that you always have to keep in your mind. So this is called as an XOR gate. So for this XOR gate, we are going to keep a NOT gate here. Then this is equal to XOR with the NOT gate is nothing but XNOR gate. So this is XNOR gate. So simply we can write the circuit like this also, XNOR gate with a feedback. So this both the circuits are same because XOR with the NOT gate is nothing but XNOR gate. So now keep the XNOR gate and there is a feedback from output to input. So both the circuits are identical. So now what is going to happen? Suppose if the input C, there is an input C here. Suppose if I make C is equal to 0, then what is going to happen? See, whenever I make C is equal to 0, then what is going to happen? I already told you in an XOR gate. So in an XOR gate, I already told you if this is X, here also X. Whenever this is 0, if this is X means here also X. So therefore simply we can say it is going to behave like a buffer. So it is going to behave like a buffer. So this is a buffer and this is a NOT gate. So you can see clearly if this is X, here also X, but now X complement. So therefore then what you are going to get, if you analyze the circuit, you can see one important point. Suppose if the output is 0, I have already told you this is a buffer. So same output you are going to get here also 0. So 0 complement is again 1. If this is 1 here, then what is going to happen? Here also 1. So 1 complement is again 0. You can see output is changing continuously 0, 1, 0, 1 like that. So we can say there is no stable state. So this is called as the astable multivibrator. So this is called as the astable multivibrator. So this circuit is going to behave like a astable multivibrator. So that is the reason I have written here AMV, astable multivibrator. So whenever you give C is equal to 0, whatever this input same is going to become output. So it is going to behave like a buffer. So this is going to behave like a buffer. So if this is 0, here also 0, here also 0. Again 0 complement is 1. So you can say continuously there is a change in the output. So it is called as that. So it is called as the astable multivibrator because there is not even any stable state. So because of that reason it is called as the astable multivibrator. Suppose what happens when C is equal to 1. So when C is equal to 1, then what is going to happen? I have already told you if C is equal to 1, if this is the X, then this will be X bar because it is going to behave like a NOT gate. So therefore this is X bar, this has become now X bar. So then you can see simply I have already told this is going to behave like a now NOT gate. So it is going to behave like a NOT gate. So now if you do the analysis, so both NOT gates means we are going to become a buffer. So if we are going to get a buffer means same thing, not all the input same as the output. So we are going to get two stable states. That is the reason it is called as a bistable multivibrator. So let me explain with a small, we can say like this analysis. Suppose if the output is 0, here also 0, 0 complement is again 1, 1 complement is 0, again here it is 0, again here it is 1, again here it is 0. So you can say output is always stable. If the output is 0, it will always stay for 0 for all the time. So it is called as the stable state. Suppose if the output is 1, what happens? Again here input is 1, so 1 complement is again 0, again 0 complement is 1, again 1 comes here, again 1 complement is 0, again 0 complement is 1. So you can say always you are going to get the output as stable output. Suppose if the output is 0, it will always remains at that position for all the time. If the output is 1 means it will remain at that position for all the time. So you have two stable states. So that is the reason it is called as the bistable multivibrator, because it has two stable states. So that is the reason it is called as the bistable multivibrator. But there is not even any stable state. So because of this reason only it is called as the unstable multivibrator. But here you can get two stable states. So it is called as a bistable multivibrator. Now you can see clearly there are basically four diagrams. You can see clearly these are the very important diagrams, because in the questions they are going to directly ask the questions based on this. Suppose there is a JK flip-flop like this. There is a J, this is a K. So K I am going to give to 1, and this is the Q, and this is the Q bar. So from Q bar I am taking a feedback and I am going to give to J. If the clock frequency is F, then what is the frequency of Q? The frequency is equal to F by 2. So this is an important point that you always have to remember. See, at this condition, at this graph, when K is equal to 1 and input of J is equal to Q bar, then the frequency of the Q is nothing but half of the clock frequency. So now there is another circuit. Then you can go for JK flip-flop or SR flip-flop. So now if you take the feedback of J from Q bar and if you take the feedback of K from Q, then if the clock frequency is F, then the frequency of the Q is nothing but F by 2. Similarly for T flip-flop, if input we are going to keep it as 1 in the toggling condition, in the resurrect condition, then definitely if you give a clock frequency of F, then the Q and Q bar, so Q and Q bar both having the same frequency, which is F by 2. If Q is F by 2 means Q bar is also same thing, F by 2. So for all these things, if Q is F by 2 means Q bar is also F by 2. Similarly, there is another circuit for D flip-flop. For D flip-flop, I have taken input of D from Q bar, and if I given a clock as a frequency of F, then the frequency of both Q and Q bar has the same frequency, which is F by 2. So these are the important four diagrams that you always have to keep in your mind, because in the examinations they are going directly ask the questions from this one. So therefore, out of this any circuit, they are going to give the circuit and they are going to ask what is the frequency at this Q. So therefore, you can say clearly, whenever for this JK flip-flop, if you take a feedback from J to Q bar, and if you give K to Q, K is equal to 1, the frequency of both Q and Q bar is nothing but F by 2, which is F is the supply, the clock frequency. Similarly, if it is a JK flip-flop or SR flip-flop, if you take input from J from Q bar and K from Q, then if the clock has a frequency of F, then the frequency of both Q and Q bar is equal to F by 2. Similarly for T flip-flop, if you operate the T in the one condition is toggling mode, then for Q and Q bar, the clock frequency is F, then the output Q and Q bar has the same frequency, which is F by 2. Similarly, for D flip-flop, if you take a output from D to Q bar, and already told you if you take a feedback from Q bar to D is something but it is a, if you have more flip-flops like that, it is called as a Johnson's ring counter. I have already told you, if you have like a counter, like group of flip-flops, it is called as a counter. So therefore now you can see clearly, if the clock has a frequency of F, then the frequency of Q is nothing but F by 2. So these are the graphs that you always have to keep in your mind. You can see clearly. So now we will discuss one of the important points regarding the digital electronics. The minimum logic gates for a given logical expression is minimum logic gates is SOP or POS in minimized form. So we can say the minimum logic gates for a given logical expression is minimum logic gates in SOP or POS minimized form. So the minimum logic gates for a given logical expression is minimum logic gates in SOP or POS minimized form. So basically here, what is that telling is the minimum logic gates for a given logical expression is the minimum logic gates in SOP or POS minimized form. So suppose they are going to give you some logical expression and they are going to ask you how many number of minimum logic gates are going to require to make this expression to become true. So therefore, first you have to do the minimize of the canonical expression that you have given. So try to do the minimized as simple as possible. You try to do the minimize as simple as possible. So whatever the expression that you are going to get in either sum of products or the product of sum, so SOP or POS, the resultant whatever the expression that you are going to get is in minimized form and it is going to have the minimum logic gates in it. So we can say The minimum logic gates for a given logical expression is minimum logic gates in SOP or POS minimized form. So what I am trying to tell you, see whatever the logical expression that they have given, so first thing is that you have to minimize it. So if you minimize it, then you are going to get very simple expression, and that simple expression can be either in the SOP or POS minimized form. And now try to figure out the minimum logic gates required for this simplified expression. So then whatever is canonical expression we can easily represent with the help of this minimum logic gates. So we can say the minimum logic gates for a given logical expression is minimum logic gates in SOP or POS minimized form. So therefore the minimum logic gates for a given logical expression is minimum logic gates in SOP or POS minimized form. So the minimum logic gates for a given logical expression is the minimum logic gates in SOP or POS minimized form. So now the next statement is for n variables. For n variables, 2 to the power of n truth tables possible or logical expressions possible. I want to tell you one important point. For n variables, you are going to get 2 to the power of n combinations. So for 2 to the power of n combinations, so 2 to the power of n combinations means each has a 2. So again 2 to the power of n truth tables are going to be possible. So 2 to the power of n truth tables means this number of logical expressions have been possible with the help of n variables. So I want to tell you, with the help of n variables, you are going to get 2 to the power of n combinations. So again, for this 2 to the power of n combinations are going to act like variables. So again, you are going to get 2 to the power of n logical expressions or truth tables that we are going to get here for this case. So always you have to remember in this fashion. So therefore, for n variables, so for n variables, you are going to get 2 to the power of n truth tables are possible or logical expressions are possible. So for n variables, 2 to the power of n truth tables possible or the logical expressions possible. Once clearly here, for n variables, you are going to get 2 to the power of n combinations. So for 2 to the power of n combinations, then we are going to get 2 to the power of n variables. So for n variables, you are going to get 2 to the power of n combinations. So it is going to act like, so you have to take this one again, 2 to the power of this value. So here n is there, so you have to take 2 to the power of this value we have to take, just 2 to the power of n. And for here 2 to the power of this value we have to take, just 2 to the power of 2n. So you can see for n variables, the number of combinations are 2 to the power of n, and for this 2 to the power of n combinations, we are going to get 2 to the power of n logical expressions or truth tables that we are going to get in this format. So you can see clearly from this, we can say simple visualization, we can easily understood that for n variables you are going to get 2 to the power of n combinations, and for this 2 to the power of n combinations, then we are going to get corresponding 2 to the power of n. We can say basic logical expressions or the truth tables that we are going to possible. Next statement is for n variables 2 to the power of n minus 1 logical expressions are self-dual. So out of these overall 2 to the power of n truth tables, out of these 2 to the power of n minus 1, these main logical expressions are self-dual. So we can say for n variables 2 to the power of n minus 1 logical expressions are said to be self-dual. So we can say for n variables, 2 to the power of n minus 1 logical expressions are said to be self-dual. So we can say clearly for n variables 2 to the power of n minus 1 logical expressions are self-dual. Self-dual means I have already told you f of duality is equal to dual. So if you do the duality of a function, if you get the same function f, it is said to be a dual function, self-dual function. So therefore for n variables you are going to get 2 to the power of n minus 1 logical expressions are said to be self-dual. Self-dual means I have already told you the duality of a function, if it is equal to the function, then it is said to be a self-dual. So the next statement is in TTL open input terminal or unconnected input terminal is going to act like logic 1. So in TTL, whatever the open input terminal or unconnected input terminal, it is going to act like logic 1. These things also I have already told you. So basically in the TTL open input terminal or unconnected input terminal, which is going to act like logic 1. So I have already told you in the TTL logic family, in a TTL logic family, if one of the input terminal is open circuited or if it is not connected to anything, it is going to act like a logic 1. So we can say in a TTL logic family, open input terminal or unconnected input terminal is going to act like logic 1. Whereas in the ECL logic family, open input terminal or the unconnected input terminal, it is going to act like logic 0. So in a ECL logic family, whatever the open input terminal or the unconnected input terminal, it is going to act like logic 0. Whereas in the TTL, the open input terminal or unconnected input terminal is going to act like logic 1. Whereas in the ECL logic family, the open input terminal, it is going to act like the or unconnected input terminal is going to act like logic 0. So this is a very important point that you always have to keep in your mind. So for TTL logic family, the open input terminal or unconnected input terminal, it is going to act like logic 1. Whereas in the ECL logic family, the unconnected input terminal or the open input terminal is going to act like logic 0. So this is the key difference that you always have to keep in your mind regarding the TTL and also ECL. So in the TTL, open input terminal or the unconnected input terminal, it is going to act like logic 1. Whereas in the ECL logic family, open input terminal or the unconnected input terminal, it is going to act like logic 0. So next point is SOP circuits can be realized with minimum NAND gates. I have already told you sum of min terms. Then we can say SOP means sum of product terms. Sum of product terms can be realized with minimum NAND gates. So SOP circuits can be easily represented with the minimum NAND gates. So SOP circuits can be realized with minimum NAND gates, whereas the POS circuits can be realized with minimum NOR gates. So this is an important difference that you always have to keep in your mind. So therefore, the sum of product circuits can be realized with minimum NAND gates, whereas the POS circuits can be realized with minimum NOR gates. So SOP circuits can be realized with minimum NAND gates, whereas the POS circuits can be realized with minimum NOR gates. So SOP